Please subscribe to support the channel. A star is on a collision course with our solar system. Not a comet, not an asteroid, but an entire star, billions upon billions of tons of burning plasma, moving silently across the galaxy with only one destination in its path, our cosmic neighborhood. This isn't science fiction. This isn't some distant hypothetical dreamt up in a movie script. This is real astrophysics, grounded in precise measurements and cutting-edge space observatories. And the star that carries this ominous title? Its name is Gliese 710. The very thought of a star heading toward us sparks an almost primal sense of unease. The stars have always felt untouchable, fixed in the night sky like eternal lanterns. But the truth is far more unsettling. Stars move. They don't sit still, frozen in place for eternity. They orbit the center of the Milky Way, just like our sun does, each following its own path through the great galactic dance. And in that celestial waltz, sometimes stars pass dangerously close to each other. For Earth and our solar system, Gliese 710 is the biggest cosmic bullet with our name on it. Now, when people hear that a star is headed our way, the first instinct is fear. Fear of fire raining down from the heavens, fear of collision, fear of total destruction. But like all great stories in astronomy, the reality is both more nuanced and more fascinating. This won't be a Hollywood-style star crash. Instead, the threat Gliese 710 poses is indirect. Through its gravity, through its influence on the vast icy halo that surrounds our solar system, and through the chain reaction it could unleash. The drama here lies not in the star smashing into us, but in the way it might turn the outer edges of our cosmic backyard into a firing range, pelting the inner planets with icy missiles. The suspense builds when you realize just how certain scientists are about this future encounter. We are not talking about speculation. This isn't a what-if. Using data from the European Space Agency's Gaia mission, astronomers have calculated Gliese 710's path with astonishing accuracy. The timeline is set. The trajectory is mapped. Unless some profound cosmic accident alters its course, the future rendezvous is inevitable. And when it happens, it will be the closest star to ever pass by our solar system in recorded astronomical predictions. Why does this matter to us today, when the event is still over 1 million years away? Because studying Gliese 710 isn't just about curiosity. It's about understanding the dynamics of our galaxy, the fragility of our planet, and the constant interplay between cosmic forces that could one day rewrite life's story on Earth. The threat it represents isn't immediate, but it is monumental in scope. It is a reminder that Earth, for all its beauty and stability, is not as sheltered as we like to believe. We live under the dome of a dynamic, ever-changing universe, one where stars move like ships through the night, and sometimes those ships drift dangerously close to our shores. Gliese 710 is, without doubt, the most important stellar encounter awaiting us in the foreseeable future. 1 million years may seem impossibly distant, but in astronomical terms, it is just the blink of an eye. When this star approaches, it will not just be an event in the sky. It could reshape the architecture of our solar system's outer boundary and send ripples of danger all the way down to our blue world. And so, our journey begins, unraveling the science, the history, the dangers, and the extraordinary cosmic ballet that makes Gliese 710 not just another in the sky, but the biggest known stellar threat to our planet's future. Gliese 710. The very name may not sound intimidating, almost clinical in its designation, like a catalog number on a library shelf. But hidden behind that unassuming label lies a star whose journey through the galaxy will one day put it on a direct path toward our cosmic backyard. Before we dive into the dangers it poses, we need to truly understand what this star is, where it resides today, and why astronomers pay such close attention to it. Gliese 710 belongs to a class of stars known as K-type dwarfs. Now, let's pause for a moment and unpack that. When astronomers talk about stars, they classify them by something called spectral type, a system that divides stars based on their color, surface temperature, and other properties. The sequence goes O, B, A, F, G, K, and M, with O being the hottest, bluest, and rarest stars, while M are the coolest, dimmest, and most common. Our Sun, for example, sits in the G-type category. That means it's hotter and brighter than Gliese 710, but not nearly as hot as the massive O or B stars that burn blue and live fast before dying young in supernovae. Gliese 710, as a K-type dwarf, is a notch cooler and dimmer than our Sun. These stars are often described as orange dwarfs, because when you look at them with the right instruments, they radiate a distinct orange hue. Their surface temperatures typically range from about 3,900 to 5,200 Kelvin, compared to the Sun's 5,778 Kelvin. That difference in temperature makes Gliese 710's light softer, less intense, and tinted more toward orange than the white-yellow glow of our Sun. Despite being smaller and less powerful, stars like Gliese 710 play an important role in our galaxy. In fact, K-type dwarfs are thought to be some of the most stable and long-lived stars in the universe. Where our Sun has a main sequence lifetime of about 10 billion years, a K-type dwarf can shine steadily for 20 to 30 billion years, maybe even longer. To put that in perspective, the universe itself is only about 13.8 billion years old. That means many K-type dwarfs that formed early in the history of the cosmos are still alive today, glowing quietly across the vastness of space. But what about Gliese 710 specifically? This star sits in the constellation Serpens, a faint but fascinating constellation in the northern sky. Serpens itself is unique among constellations because it's divided into two separate parts: Serpens caput, the head of the serpent, and Serpens cauda, the tail of the serpent, with the constellation Ophiuchus, the serpent bearer, running between them. Gliese 710 lies within this serpentine figure, like a scaled intruder winding its way across the heavens. It may not be one of the brightest stars you can see with the naked eye, but through telescopes and precise instruments, it's there, marking its place as a future interstellar traveler through our solar neighborhood. The Gliese designation itself comes from a famous catalogue compiled by the German astronomer Wilhelm Gliese, who dedicated much of his career to mapping the stars nearest to Earth. The Gliese catalogue of nearby stars, first published in 1957, is a cornerstone in modern stellar astronomy. It lists hundreds of stars within about 80 light-years of our Sun, giving them designations like Gliese 581, Gliese 876, and, of course, Gliese 710. These catalogue numbers might not sound glamorous, but they're vital for astronomers trying to keep track of the ever-shifting stars around us. Now, one might ask, what makes Gliese 710 stand out among the countless orange dwarfs scattered across our galaxy? After all, the Milky Way is filled with K-type stars, many of which are closer to us and brighter than Gliese 710. The answer lies not in what it is today, but in where it is going tomorrow. Most stars wander through the galaxy without ever posing a problem to us. But Gliese 710, by sheer cosmic coincidence, is on a trajectory that will bring it closer to Earth than any other known star in the foreseeable future. To appreciate this, consider that when astronomers discovered its motion and trajectory, they didn't just find another quiet orange dwarf, they found a ticking clock, counting down to a rendezvous with our solar system. Even though it currently rests comfortably at a distance that seems safe, the very fact that it is drifting toward us with such certainty transforms it from a mere point of light into one of the most important celestial objects for future humanity. Another fascinating point, Gliese 710 has been studied not only for its trajectory but also for its stellar characteristics. It has a luminosity, brightness, lower than our Sun's, which is exactly what we'd expect from a K-type star. Its smaller size and lower temperature mean it does not radiate nearly as much energy. For life-bearing planets, if any orbit Gliese 710, this would mean the habitable zone, the sweet spot where liquid water could exist, would be much closer to the star compared to our Earth-Sun distance. That fact in itself is intriguing, because many astronomers think K-type dwarfs may be some of the most promising stars to host habitable exoplanets, thanks to their stability and long lifespans. However, there's no evidence yet that Gliese 710 has planets orbiting it. If it does, they remain undiscovered, hidden against the background of its faint orange glow. But from a purely astronomical standpoint, what matters most isn't whether it has planets. It's the star's trajectory, its journey across the Milky Way, and its ultimate rendezvous with our solar system. When we talk about Gliese 710, we're not just talking about a faint orange star in Serpens. We're talking about a future neighbor, a cosmic visitor that will not simply drift by unnoticed. It will leave a fingerprint on the architecture of our solar system, rippling through the icy shell of the Oort Cloud, and potentially reshaping the story of Earth itself. It's important to grasp this duality. On the one hand, Gliese 710 is ordinary, a small orange dwarf, dimmer and smaller than the Sun, quietly burning hydrogen like countless other stars. On the other hand, it is extraordinary, because its path aligns with ours in a way that makes it an agent of possible chaos millions of years from now. That tension between the ordinary and the extraordinary is what makes this star so captivating to astronomers and storytellers alike. So when we introduce Gliese 710, we aren't simply listing its spectral type or its place in a constellation. We're setting the stage for a cosmic encounter that will one day transform this quiet little orange dwarf into the most disruptive star Earth has ever known. When we peel back the layers of mystery surrounding Gliese 710, we find that at its heart, it's a relatively small and modest star by galactic standards. Yet its true power lies not in sheer brilliance, but in the subtle gravitational influence it will one day unleash on our solar system. To understand this better, let's look closely at its basic physical facts: its mass, size, brightness, and how it compares to our Sun. Stars are usually described by comparison to the Sun, because the Sun is the one star we know intimately. It's our yardstick, our reference point. So when astronomers say Gliese 710 is a K-type dwarf, they already mean it falls into a category cooler, smaller, and dimmer than the Sun. But let's break down the numbers to see just how different the two stars really are. First, mass. The Sun's mass is the benchmark, defined as one solar mass, m. Gliese 710 has a mass estimated to be about 0.6 solar masses. In other words, it's only a little more than half the mass of our Sun. That might not sound like a huge difference, but in astrophysical terms, mass dictates nearly everything about a star's destiny: its brightness, temperature, lifespan, and eventual death. Because Gliese 710 has less mass, its nuclear furnace burns more slowly, producing less energy but also lasting much longer than our Sun will. While our Sun will exhaust its hydrogen fuel in about 10 billion years, Gliese 710's lower mass allows it to sip its fuel gradually, giving it a lifespan potentially more than twice as long. Next, size. With less mass comes a smaller radius. The Sun's radius is about 696,000 kilometers. Gliese 710's radius is about 67% that of the Sun's, or roughly 470,000 kilometers. So if you placed Gliese 710 next to the Sun, it would look noticeably smaller, a more modest orange sphere beside our golden yellow giant. Now let's talk about brightness, one of the most striking differences between the two. The Sun has a luminosity of one solar luminosity, L, by definition. Gliese 710, by comparison, has a luminosity of about 0.09 L, or only 9% as bright as the Sun. This is why Gliese 710 is not visible to the naked eye despite being a relatively nearby star in galactic terms. It simply doesn't emit enough light to shine brightly in our skies today. Through a telescope, however, it reveals its orange glow, a softer, gentler light compared to the piercing brilliance of our Sun. The difference in surface temperature also adds to its character. The Sun's surface temperature is about 5,778 Kelvin, giving it a bright white-yellow light. Gliese 710's surface temperature is estimated at around 4,000 Kelvin, which shifts its glow toward orange. This orange tint is a visual hallmark of K-type dwarfs. It's neither the searing blue-white of massive O and B-type stars nor the deep red of cooler M-dwarfs, but rather a warm, steady orange that places it in between. These physical differences also affect how life might evolve on planets orbiting stars like Gliese 710. If it had planets, their habitable zone, the region where liquid water could exist, would be much closer to the star than Earth is to the Sun. Where Earth sits at 1 astronomical unit, AU, from the Sun, a habitable planet around Gliese 710 would likely need to orbit at only 0.3 to 0 Australian dollars and 50 cents, much closer in, because the star emits less heat. This makes for fascinating speculation about whether Gliese 710 could harbor its own worlds with the right conditions for life. But for now, no planets have been confirmed orbiting it. Another striking point is longevity. Gliese 710 is essentially a star built for endurance. Our Sun will eventually swell into a red giant, then shed its outer layers, leaving behind a white dwarf. That will happen in about 5 billion years. But Gliese 710, thanks to its smaller mass and slower fuel consumption, will still be shining when the Sun is long gone. It is part of a stellar population designed by the cosmos to last practically forever on human timescales. This makes it one of the many immortal stars in the galaxy, quiet, steady, and enduring. And yet, despite its quiet nature, Gliese 710 will have one of the most dramatic effects on our solar system of any star in history. This is the irony. A star that is smaller, dimmer, and weaker than the Sun in so many respects is destined to become the most disruptive interstellar visitor in Earth's recorded astronomical future. Its power won't come from dazzling light or scorching heat, but from its gravity, tugging silently on the icy edges of our solar system and potentially altering the fate of worlds. To put these comparisons in simple terms. A mass. Gliese 710 is 60% the Sun's mass. A size. About 2/3 the Sun's radius. A brightness. About 1/10 as bright as the Sun. A temperature. Roughly 1,700 degrees cooler. A color. A steady orange, instead of yellow-white. On its own, Gliese 710 would seem like just another faint star catalogued among billions. But because of its trajectory, these modest statistics take on a cosmic weight. Its small size and dim glow mask the fact that in about 1.3 million years, it will be the closest star to pass near us, closer even than Proxima Centauri, the closest star we know today. Its basic properties remind us that power in the cosmos doesn't always come from brilliance, but from position, timing, and gravitational pull. So while Gliese 710 may seem unimpressive compared to our Sun, dimmer, smaller, cooler, it is precisely this unassuming star that will one day leave a mark on the solar system greater than any other known stellar neighbor. Right now, at this very moment, Gliese 710 is far enough away that it poses no immediate danger. It is currently located at a distance of roughly 63 light-years from Earth. For most people, numbers like this don't carry much weight, because human beings are not wired to intuitively understand cosmic scales. So let's slow down here and try to make sense of what 63 light-years really means. A light-year is the distance light travels in a single year. Since light moves at about 299,792 kilometers per second, that's around 186,000 miles per second. In 1 year it manages to cover nearly 9.46 trillion kilometers, about 5.88 trillion miles. That means when we say Gliese 710 is 63 light-years away, we're saying that the light leaving this star tonight will not reach Earth until the year 2088. The photons from Gliese 710 currently entering our telescopes have been traveling through the void of interstellar space since around the time the US was in the middle of the Cold War. That's how far away it still is. In cosmic terms, however, 63 light-years is close. The Milky Way galaxy itself spans 100,000 light-years across, and our nearest stellar neighbor, Proxima Centauri, sits only 4.24 light-years away. So while Gliese 710 is not next door, it's certainly part of our local stellar neighborhood. Imagine the galaxy as a sprawling city, with most stars spread across vast cosmic suburbs. At 63 light-years, Gliese 710 is like a house a few blocks down the street. Still distant, but close enough that when it decides to move closer, it matters. One thing that makes Gliese 710's current distance particularly interesting is how faint it is to us despite being relatively nearby. With a luminosity only about 9% of the Sun's, it doesn't stand out in the night sky. In fact, you need a telescope to see it at all. The human eye simply isn't sensitive enough to pick out such a dim, orange glow from that distance. If our Sun were replaced by Gliese 710 tomorrow, Earth would freeze almost instantly, plunged into a dim twilight forever. That contrast between the familiar brightness of our Sun and the feeble glow of Gliese 710 helps us appreciate why this star doesn't dominate the night sky despite being one of our near neighbors. Astronomers measure this distance, 63 light-years, with incredible precision thanks to space observatories like Gaia, which maps stars in 3 dimensions with milliarcsecond accuracy. To give you an idea, a milliarcsecond is the width of a coin seen from thousands of kilometers away. That's the level of detail scientists are working with when they determine how far Gliese 710 is from us and where it's heading. Without such precise measurements, we wouldn't even know that this star is creeping closer with every passing moment. Now, let's put this distance into a perspective that feels more grounded. At its current position, Gliese 710 is about 600 trillion kilometers away from Earth. That number is so vast it borders on meaningless for our daily lives, but we can break it down. The Voyager 1 spacecraft, the farthest human-made object from Earth, has been traveling for more than 45 years and is only about 24 billion kilometers away. Even at that astonishing achievement, Voyager has barely scratched the surface of interstellar distances. To reach Gliese 710 at its current distance, Voyager would have to travel for 25 million years at its present speed. That's how far away 63 light-years truly is in practical terms. Despite this immense distance, Gliese 710's motion toward us is steady and relentless. It is part of the Milky Way's disk, orbiting the galactic center just like our Sun. But unlike most of our neighboring stars, its orbit will carry it straight toward us. Slowly, invisibly, over millennia, the gap between our solar system and this orange dwarf is shrinking. At the current measured velocity, it's not a matter of if it will get close, it's a matter of when. There's also something fascinating about how astronomers detect this approach. They don't just look at how bright the star is or where it sits on the celestial map. They measure its radial velocity, how fast it's moving toward or away from us, and its proper motion, how it shifts sideways across the sky relative to background stars. Combine those two, and you get a three-dimensional trajectory. For Gliese 710, both numbers show the same story. It is heading directly for the solar system's outer reaches, like a slow-moving ship on a predestined course. This also makes Gliese 710 an example of how astronomy often deals with paradoxes of scale. On one hand, it is unimaginably far away, so far that we can't comprehend traveling there with today's technology. On the other hand, it is close in galactic terms, so close that its flyby will be the closest stellar encounter predicted in the next few million years. Its 63 light-year starting distance will collapse to less than a tenth of a light-year when the encounter happens. From hundreds of trillions of kilometers down to only a trillion. That's like watching a tiny dot on the horizon slowly grow into a mountain. In essence, Gliese 710 today is a faint star quietly burning in the constellation Serpens, far enough that it poses no danger. But astronomically speaking, it's in the fast lane of the galaxy, and its trajectory has been measured with precision. We know where it is, we know where it's going, and we know that every year it inches closer to us. Right now, its presence feels remote and almost academic. But given enough time, this vast distance will shrink dramatically, and the true significance of Gliese 710's approach will reveal itself. For now, we look at Gliese 710 from afar, aware that its story is not about the present but about the future. Its 63 light-year separation is a safe cushion, but not a permanent one. Every star you see twinkling in the night sky is moving. Some drift lazily across the heavens, others hurtle through the galaxy at breakneck speeds, but none of them are fixed. The notion of a fixed star is a relic from ancient times, when early astronomers believed the heavens were a perfect, unmoving dome. In reality, our galaxy is a vast, dynamic system, and the stars are like ships on a cosmic ocean, each tracing its own route around the galactic center. Our own Sun is part of this dance. It orbits the Milky Way's core at an average speed of about 828,000 kilometers per hour, 514,000 miles per hour, taking roughly 225 million years to complete a single orbit, one galactic year. Every other star you see is also in orbit, moving on paths influenced by the combined gravitational pull of the galaxy. These paths can vary dramatically, and as they cross, stars sometimes pass close to one another. Not often, on the scale of millions of years, but often enough that we know stellar flybys are a natural part of galactic life. Gliese 710 is one such traveler. At this moment, it is quietly making its way across the constellation Serpens, carried by the galactic currents. Unlike some stars that orbit with motions keeping them well away from us, Gliese 710's path is different. Its orbit intersects with ours in such a way that it will come unnervingly close to our solar system. Think of it like two cars driving around a massive roundabout. For most of their paths, they stay far apart, but eventually, one takes a turn that brings it dangerously close to the other. The trajectory of Gliese 710 is not guesswork, it is a product of careful measurement. By tracking its proper motion, its sideways drift across the sky relative to distant background stars, and its radial velocity, how quickly it is moving toward or away from us, astronomers can calculate its three-dimensional trajectory with remarkable precision. The result is clear. Gliese 710 is on a course that will bring it closer to us than any other known star in the next few million years. It's important to remember that stars don't move in straight lines forever. Their paths are curved by the overall gravitational influence of the Milky Way. But when you zoom in on the relatively short timescales of a few million years, their motion looks like a straight shot across interstellar space. For Gliese 710, That straight shot happens to be angled directly toward our solar system. What makes this especially dramatic is that stellar encounters like this are rare on human timescales. The vast majority of stars in our local galactic neighborhood never come anywhere close to our Sun. They wander past at safe distances, hundreds of light years away, barely influencing us at all. Yet here we are, with Gliese 710 charting a course that will bring it into our outer solar system, closer even than Proxima Centauri is today. You might imagine stars crashing into each other all the time in a crowded galaxy, but the truth is space is overwhelmingly empty. The Milky Way may contain over 200 billion stars, yet the average distance between them is several light-years. The odds of two stars colliding are vanishingly small, but the odds of them passing near one another, close enough for gravitational interactions, are much higher. And when near in astronomy means a fraction of a light-year, it can have profound consequences for planetary systems like ours. Gliese 710's journey toward us is slow on human timescales, but relentless. With every passing year, it inches closer, though we can't perceive that motion with the naked eye. To us, it looks like just another faint star fixed in the sky. But over tens of thousands of years, its position changes slightly, like a ship on the horizon that gradually grows larger. And in about 1.3 million years, its path will bring it to its closest approach, a near miss in cosmic terms, but a very significant one for the solar system. One way to picture this is to imagine Earth standing still while Gliese 710 drifts toward us across the dark sea of space. It won't crash into us, but its gravitational wake will be enough to disturb the delicate balance of icy bodies surrounding our Sun. That's the key difference here. It's not about a star colliding with Earth or the Sun, but about how its path through the galaxy intersects with ours in just the right way to cause trouble. It's also worth noting that Gliese 710 is not alone in having such a path. Astronomers have identified many stars that will pass near the solar system at some point. But among all of them, Gliese 710 is the closest and most certain encounter in our foreseeable future. Its trajectory is so well measured that scientists can say with confidence, yes, this star is coming, and yes, it will pass close enough to matter. And so we arrive at the chilling truth. Gliese 710 is not extraordinary because of its size, brightness, or heat. It is extraordinary because of its motion, because its path through the galaxy intersects directly with ours. Among billions of stars, this orange dwarf happens to be aimed at us, not to collide, but to graze our cosmic neighborhood in a way that will leave deep and lasting consequences. For now, it continues its slow march, unnoticed by all but astronomers with precise instruments. But make no mistake, its course is set. Gliese 710 is a traveler whose journey is leading it straight to our doorstep. The future of our solar system has already been written into the stars, and one chapter of that future carries the name Gliese 710. Astronomers, using the most advanced measurements of stellar motion ever collected, have marked a date in the deep future. About 1.3 million years from now, this modest orange dwarf will sweep past our solar system in one of the closest stellar encounters ever predicted. Now, 1.3 million years may sound like an eternity. To us, bound by human lifespans measured in decades, it feels inconceivably distant. Civilizations rise and fall in mere thousands of years. Human history itself, the span of all recorded events, is less than 6,000 years. Even our species, Homo sapiens, has only existed for around 300,000 years. Compare that to 1.3 million years, and the timescale stretches into something almost mythical. Yet in cosmic terms, this is practically tomorrow. Stars live for billions of years. Galaxies evolve over tens of billions. On that grand scale, 1.3 million years is less than a blink, a fleeting moment. So what will actually happen in this moment of cosmic closeness? Calculations show that Gliese 710 will not collide with the Sun or with Earth. Instead, it will pass by at a minimum distance of about 0.06 to 0.08 light-years. That translates to roughly 14,000 to 20,000 astronomical units, AU. For comparison, Pluto, our most famous dwarf planet, orbits at only about $40 from the Sun. The farthest human-made spacecraft, Voyager 1, is about $160 away. So when Gliese 710 makes its closest approach, it will be hundreds of times farther than Pluto, thousands of times farther than Voyager, but still close enough to slice through the icy boundary of our solar system. That boundary is the Oort Cloud, the distant sphere of icy bodies surrounding us like a fragile halo. Gliese 710's encounter will happen well within this region, which stretches from about $2,000 to perhaps $100,000. When the star passes by, its gravity will stir the Oort Cloud like a giant spoon swirling a bowl of cosmic ice cubes. Many of those icy bodies, comets in waiting, will be nudged out of their quiet orbits and sent tumbling toward the inner solar system. But more on the Oort Cloud and comets later. For now, the key takeaway is this. In about 1.3 million years, Gliese 710 will sweep past our solar system at a distance so close, astronomically speaking, that it will become the most significant stellar visitor we know of in the near future. It's worth pausing here to appreciate the confidence with which scientists make such predictions. How can we possibly know what will happen more than a million years from now? The answer lies in the precision of astronomical measurements. Using instruments aboard the Gaia spacecraft, astronomers have tracked Gliese 710's motion with exquisite detail. Gaia measures the positions, distances, and movements of over 1 billion stars, mapping the Milky Way in 3 dimensions with unprecedented accuracy. For Gliese 710, the data is so precise that its future trajectory has been charted like a bullet fired across space. Unless some massive, unforeseen gravitational influence alters its path, its course toward our solar system is essentially guaranteed. Of course, there are always uncertainties in science. The exact closest approach distance may vary slightly depending on new measurements. Some models put the encounter at 0.06 light-years, others at 0.08. The difference might not sound like much, but in astronomy, those tiny changes can alter the severity of the gravitational effects. A closer pass would stir the Oort Cloud more violently, sending more comets inward. A slightly farther pass might cause less disruption. But in all scenarios, the encounter will be profound. Now imagine what the sky might look like in the year of Gliese 710's arrival. As the star nears its closest point, it will brighten dramatically in our night sky. Today, it is invisible without a telescope, but when it approaches within 1.3 million years, it will shine as one of the brightest stars visible to the naked eye. From Earth, it will appear like a brilliant orange beacon in Serpens, impossible to miss, a celestial warning light heralding its disruptive influence on the solar system. What makes this event so extraordinary is that we can already place it in a timeline. While so much of the universe feels unpredictable and chaotic, this is something astronomers can pinpoint. In 1.3 million years, a star will pass close enough to jolt the outer solar system. We know its arrival date. We know its distance. We even know the likely consequences. Think about that for a moment. In the deep future, when human civilization may look utterly different, or perhaps no longer exist, this cosmic event will still unfold exactly as predicted. Gliese 710 is a reminder that the universe keeps its own clock, a timescale far beyond human history, yet one we can read with remarkable precision. So the timeline is set. In about 1.3 million years, Gliese 710 will glide past the Sun's outer frontier. It will not burn us, it will not collide with us, but its gravitational whisper will be loud enough to echo through the solar system for millions of years afterward, in the form of comets raining down toward the inner planets. We stand here today, 63 light-years away from the star, knowing the clock is ticking. Slowly, inevitably, Gliese 710 is making its way toward us, a silent traveler whose arrival has already been penciled into the future history of Earth. When astronomers talk about Gliese 710's future encounter with the solar system, the numbers are staggering, yet precise. The star is predicted to pass at a distance of roughly 0.06 to 0.08 light-years from the Sun. On the surface, this may sound like an incomprehensibly large gap. After all, light-years are distances so vast that our everyday intuition cannot grasp them. But in cosmic terms, this is astonishingly close. Let's translate that into units we can better picture. 1 light-year is about 9.46 trillion kilometers, 5.88 trillion miles. So when Gliese 710 approaches within 0.06 light-years, that is approximately 5.7 trillion kilometers, and at 0.08 light-years, about 7.6 trillion kilometers. While these distances are immense from a human standpoint, in astronomical terms, especially when we consider the size of the solar system, they are incredibly near. Astronomers also often measure such distances in astronomical units, AU. 1 AU is the distance from the Earth to the Sun, roughly 150 million kilometers, 93 million miles. This makes the solar system easier to map in human-friendly numbers. By converting the flyby distance into AU, we find that Gliese 710 will pass at roughly 14,000 to 20,000 Australian dollars. To put that in context, Neptune orbits at about 30 Australian dollars, Pluto at about 40 Australian dollars, and the far reaches of the Kuiper Belt extend to roughly 50 Australian dollars. The closest known star today, Proxima Centauri, is more than 268,000 Australian dollars away. So when Gliese 710 passes at 14,000 to 20,000 AU, it will come closer than any other star we currently know of, piercing deep into the outskirts of our solar system. At first glance, 14,000 to 20,000 AU might seem like a safe buffer. After all, the planets, moons, and asteroids that make up the inner solar system orbit within a tiny fraction of this distance. Earth is at 1 Australian dollar, Jupiter at 5 Australian dollars and 20 cents, Saturn at 9 Australian dollars and 50 cents. Even the farthest dwarf planets like Sedna, at its highly elliptical orbit, come no closer than around 76 Australian dollars. Yet the critical factor here is gravity, and Gliese 710's gravitational influence is powerful enough to perturb objects far beyond the planetary realm. This close approach will occur within the Oort Cloud, a vast, diffuse shell of icy bodies stretching from roughly 2,000 Australian dollars to over 100,000 Australian dollars. Gliese 710 will pass through the inner portion of this cloud, causing many of these distant, frozen objects to be nudged from their orbits. The gravitational pull will act like a giant cosmic hand, stirring up a dormant region of the solar system and potentially sending comets careening toward the inner planets. It's important to emphasize that Gliese 710 itself is not a threat to Earth in terms of direct impact. Its distance, even at its closest, is still tens of thousands of times farther than our Sun. But the secondary effects, gravitational disturbances and potential comet showers, are where the danger lies. This is why astronomers focus on not just the distance, but the relative position to the Oort cloud, because that's the region most susceptible to disruption. What makes these numbers even more fascinating is the accuracy of the predictions. Thanks to precise observations from the Gaia mission, astronomers can model the flyby to within a few thousand AU. Even small variations in the star's velocity or position today could slightly alter the distance, but in all reasonable models, it remains a near miss, close enough to make a significant gravitational impact. To put it in perspective, imagine standing in a stadium with a crowd stretching all around you. If the stadium is the solar system and Earth is in the center, Gliese 710 will pass somewhere in the outermost seats. It won't touch the playing field directly, but its presence will cause a ripple, a gravitational jostle that travels inward, disturbing everything in its reach. That's the essence of why this flyby is so scientifically significant. In short, Gliese 710's predicted distance of 0.06 to 0.08 light-years, or 14,000 to 20,000 AU, positions it as an unprecedented close encounter. It's the nearest stellar approach we expect in the foreseeable future, close enough to stir the distant edges of our solar system while remaining far enough to avoid a direct collision. Its path and distance provide astronomers with a detailed blueprint for modeling the consequences, allowing us to anticipate how the outer solar system will react millions of years from now. Before we can fully appreciate just how close Gliese 710 will come to the solar system, we need to pause and talk about a fundamental unit of measurement that astronomers use all the time, the astronomical unit, abbreviated as AU. This is one of those concepts that seems simple at first but quickly becomes essential for understanding distances in our cosmic neighborhood. An astronomical unit is defined as the average distance between the Earth and the Sun, which is roughly 149.6 million kilometers, or about 93 million miles. It's the yardstick astronomers use to describe distances within our solar system. Think of it as the cosmic equivalent of a mile or kilometer, but specifically for measuring the vast expanses between celestial objects orbiting our Sun. Using AU instead of kilometers or miles makes sense because the numbers become much more manageable. For example, saying Jupiter orbits at 778 million kilometers from the Sun is accurate, but much less intuitive than saying it orbits at 5 Australian dollars and 20 cents. Pluto, at roughly 40 Australian dollars, is easier to grasp when compared to Earth's orbit at 1 Australian dollar rather than thousands of millions of kilometers. It provides a relative framework that immediately tells us how far a planet or object is from the Sun compared to the Earth. When it comes to Gliese 710, the AU becomes even more critical for perspective. The star's predicted flyby distance is 14,000 to 20,000 Australian dollars. At first glance, those numbers may not mean much, but consider that the outer edge of the Kuiper belt, home to Pluto and other icy bodies, sits around 50 Australian dollars, and the inner edge of the Oort Cloud begins around 2,000 Australian dollars. That means Gliese 710 will pass well within the inner region of the Oort Cloud. Using AU makes it much easier to visualize. The star will come hundreds of times farther than Pluto, but still close enough to gravitationally disturb trillions of icy objects lying at the solar system's frontier. It's also helpful to compare the AU to other familiar distances. The Voyager spacecraft, the farthest human-made object, is roughly 160 Australian dollars from the Sun. That's almost 3 times the distance from the Sun to Pluto, yet it's still minuscule compared to the 14,000 to 20,000 AU distance at which Gliese 710 will pass. In other words, the star's flyby is extremely close by interstellar standards, but still staggeringly distant compared to anything humans have ever sent into space. Understanding AU also allows us to frame the gravitational effects. Gravity weakens with distance, but even at 14,000 to 20,000 AU, Gliese 710's mass, about 60% of the Sun's, is enough to perturb objects in the Oort Cloud. These icy bodies, loosely bound and spread across a huge volume, are highly sensitive to passing stars. In essence, the AU helps us scale the scenario, close enough to cause chaos in the outer solar system, far enough to leave the planets themselves largely unaffected. For many viewers, this helps make the concept more tangible. Instead of thinking in incomprehensible trillions of kilometers or billions of miles, we can picture Earth at $1 Australian, Neptune at 30 Australian dollars, and then Gliese 710 zooming past at tens of thousands of AU, a distance that is enormous in everyday terms but dangerously close in cosmic terms for our outermost icy frontier. In short, the astronomical unit is the lens through which astronomers view the scale of the solar system, from planets to asteroids to the distant reaches of the Oort Cloud. When we say Gliese 710 will pass within 14,000 to 20,000 Australian dollars, we are talking about a star coming hundreds of times farther than Neptune or Pluto, yet close enough to gravitationally stir the solar system's icy halo, a scale that is almost impossible to visualize without this handy unit. By using AU, we not only gain a practical measuring stick, but also a way to comprehend the true significance of Gliese 710's approach. It is the difference between thinking of it as really far away versus understanding it as so close that it will directly influence our solar system structure. When we talk about Gliese 710 passing within 14,000 to 20,000 Australian dollars, the numbers alone might still feel abstract. To truly grasp the significance, we need to compare that distance to the Oort Cloud, the vast, icy shell that forms the outermost boundary of our solar system. This comparison transforms the numbers into something meaningful and gives a real sense of why astronomers are paying such close attention to this stellar visitor. The Oort Cloud is a theoretical cloud of icy bodies that surrounds the Sun, planets, and Kuiper belt in a nearly spherical shell. It begins somewhere around 2,000 Australian dollars from the Sun and can extend out to as far as 100,000 Australian dollars, though estimates vary. That's a distance from the Sun of nearly 1.5 light-years at its outer edge, meaning the Oort Cloud's volume occupies a substantial portion of the space between our Sun and the nearest stars. It is, in many ways, the solar system's outermost frontier, the region where the Sun's gravitational grip is weakest and objects are most susceptible to external influences. Now let's overlay Gliese 710's predicted flyby distance onto this structure. At 14,000 to 20,000 Australian dollars, Gliese 710 will pass well inside the inner Oort Cloud, but still far outside the planetary system we're familiar with. To put it in perspective, Neptune orbits at 30 Australian dollars, Pluto at roughly 40 Australian dollars, the Kuiper belt extends to about 50 Australian dollars, and the inner Oort Cloud starts at 2,000 Australian dollars. Gliese 710 will not be scraping the planets. It will instead penetrate the icy, largely unpopulated region that extends tens of thousands of AU from the Sun. This is crucial because the Oort Cloud is extremely sensitive to gravitational perturbations. Its icy inhabitants, comets, minor planets, and other small bodies, are loosely bound to the Sun. Even a relatively small external gravitational nudge can redirect their orbits, sending some of these objects spiraling inward toward the inner solar system. In this sense, Gliese 710 is like a massive cosmic hand reaching into the outer solar system, stirring dormant material that has remained mostly untouched for billions of years. By comparison, most stars pass safely far outside the Oort Cloud, hundreds of thousands of AU away, leaving the solar system largely undisturbed. Gliese 710 is different. Its path takes it directly into the inner portion of the cloud, close enough to destabilize orbits of trillions of icy bodies. Some of these may eventually become long-period comets, traveling hundreds of millions of kilometers toward the inner planets. That's why astronomers consider this flyby extraordinary. It is one of the closest known stellar encounters with the potential to significantly influence the solar system's outer regions. Let's put it visually. Imagine the solar system as a central hub surrounded by a huge, faint sphere of ice and rock, the Oort Cloud. Most stars drift past outside this sphere, never disturbing it. Gliese 710, however, is projected to pass right through the inner portion of this shell. Its gravitational pull will act like a spoon stirring a bowl, slightly shaking the positions of countless icy bodies. Over the millennia following the flyby, some of these bodies may be flung toward the Sun, creating a cascade of comets that could intersect with the inner planets, including Earth. Another important point: while 14,000 to 20,000 AU sounds huge, in the scale of the Oort Cloud, it's relatively close. The Oort Cloud's outer edge may extend to 100,000 Australian dollars or more, so Gliese 710's passage through the inner region is akin to walking through the shallow part of a vast lake, disturbing everything within reach. In other words, the star doesn't need to get anywhere near the planets to have an effect. The icy outskirts of the solar system act as a bridge, transmitting gravitational disturbances inward over time. This is why Gliese 710's approach is described as closer than you think. From a human perspective, tens of thousands of AU are unfathomably distant. But from the perspective of the solar system structure, this is a close, potentially disruptive approach, reaching right into the territory of the Oort Cloud. The star's passage will not alter Earth's orbit directly, nor will it collide with the Sun, but its influence will ripple through the outer solar system like a gravitational shockwave. Understanding this context also highlights why astronomers are able to model the flyby with such specificity. By knowing the distance and trajectory, they can simulate the gravitational interactions between Gliese 710 and the Oort Cloud. These simulations suggest a surge of cometary activity in the distant future, an indirect but very real risk for the inner solar system. In essence, Gliese 710's flyby is a cosmic brush with our solar system's icy frontier. It will pass closer than most stars ever do, penetrate the inner Oort Cloud, and in doing so, potentially launch a new generation of comets toward the inner planets. It is a stellar encounter that is not just a distant event, but one with tangible implications for the architecture and long-term stability of our solar system. The Oort Cloud is one of the most fascinating and mysterious structures in our solar system, and understanding it is essential to grasp why Gliese 710's future flyby is such a big deal. Imagine the solar system as a set of concentric layers. Closest to the Sun, we have the familiar planets, moons, and asteroids. Beyond them stretches the Kuiper Belt, a ring of icy bodies that includes Pluto and other dwarf planets. Farther still lies the Oort Cloud, a nearly spherical shell of icy debris that forms the outermost boundary of the Sun's gravitational influence. The Oort Cloud is named after the Dutch astronomer Jan Oort, who first proposed its existence in 1950 to explain the origins of long-period comets that take hundreds of thousands to millions of years to orbit the Sun. Unlike short-period comets, which originate in the Kuiper Belt and have orbits under 200 years, long-period comets arrive from the distant reaches of the solar system, seemingly from nowhere. Their trajectories suggested a reservoir of icy bodies at extreme distances, far beyond the planets we see. That reservoir became the hypothesized Oort Cloud. Estimates place the Oort Cloud's inner edge around 2,000 Australian dollars from the Sun and its outer edge anywhere between 50,000 and 100,000 Australian dollars. To give perspective, 1 Australian dollar is the distance from Earth to the Sun, about 150 million kilometers. So even the closest portion of the Oort Cloud begins 50 times farther than Pluto. The outer edge stretches halfway to the nearest stars in our neighborhood. It's an enormous, diffuse cloud, mostly invisible and extremely difficult to study directly because its components are small, cold, and faint. Almost everything we know about the Oort Cloud comes from indirect observations, like tracking the paths of long-period comets and modeling gravitational influences. The Oort Cloud is composed mainly of icy planetesimals, remnants of the primordial material that formed the solar system. These include water ice, frozen gases, rock, and dust, basically the leftovers from the early solar nebula that didn't coalesce into planets. They are loosely bound to the Sun, meaning even a small gravitational disturbance can nudge them out of their orbits and send them careening toward the inner solar system. This is where Gliese 710 becomes a central player in the story. At a predicted closest approach of 14,000 to 20,000 Australian dollars, the star will pass through the inner region of the Oort Cloud. Its gravitational pull, although modest compared to the Sun's nearby, will be enough to disturb countless icy bodies. Imagine a swarm of leaves floating in a pond. Most remain stationary until a stick, or in this case, a star, passes nearby, sending waves through the water that shift their positions. Gliese 710 will act as that cosmic stick, stirring dormant bodies that have remained largely undisturbed for billions of years. Why is this so important? Because the Oort Cloud is effectively a time capsule and a potential hazard zone. It preserves primordial material from the solar system's formation, offering scientists clues about how planets and stars came to be. At the same time, it's a storehouse of potential comets, icy bodies that, if sent inward, could intersect with the orbits of the planets, including Earth. A disruption here doesn't happen immediately. It can take thousands to millions of years for objects to travel from the Oort Cloud to the inner solar system. But the effects are inevitable once the disturbance occurs. Gliese 710's flyby is a rare opportunity, and a rare threat. Most stars pass far outside the Oort Cloud, leaving it undisturbed. Gliese 710 will penetrate it deeply enough to increase the flux of long-period comets, some of which may eventually cross paths with Earth. Scientists model these events using advanced simulations of gravitational dynamics, and while there is uncertainty in the exact number of comets affected, the potential is enormous simply because of how dense the Oort Cloud is in terms of icy bodies. In short, the Oort Cloud acts like a cosmic warning system. It is the part of the solar system most sensitive to external influences. Gliese 710's journey may turn this quiet, distant region into a source of activity that propagates inward, generating a potential comet storm in the distant future. Without the Oort Cloud, the flyby of Gliese 710 would be largely inconsequential, just a star passing harmlessly through space. It is the Oort Cloud that amplifies the consequences, converting a distant star into a future driver of cometary chaos. So when we consider Gliese 710 approaching within tens of thousands of AU, we aren't just talking about a star moving through empty space. We're talking about a star stirring the outer reaches of our solar system, waking up icy bodies that have slumbered for billions of years and setting them on a trajectory that could eventually bring them dangerously close to Earth. This interplay between the star and the Oort Cloud is the real reason astronomers describe Gliese 710 as the biggest known stellar threat to our planet. Gliese 710's impending flyby is not a story about fire, explosions, or direct collisions. It is a story of gravity, subtle but profoundly influential. Gravity is the invisible force that binds planets to stars, moons to planets, and structures entire galaxies. Even at enormous distances, the pull of a star like Gliese 710 can affect objects far beyond its immediate vicinity, and this is exactly what will happen when it passes through the inner Oort Cloud. The Oort Cloud is a vast collection of icy bodies, loosely bound to the Sun by its gravity. The farther an object is from the Sun, the weaker the Sun's gravitational hold becomes. By the time you reach the inner Oort Cloud at around 2,000 Australian dollars, the Sun's grip is faint enough that another star passing nearby, even one smaller than the Sun, can exert a measurable tug on these bodies. Gliese 710, with its 0.6 solar masses, will pass close enough that its gravitational field will create disturbances across this massive cloud. Think of it like this. Picture a calm pond filled with floating ice cubes. Each cube is held in place by the water's gentle currents. Now, imagine a heavy object plunging through the pond nearby. The cubes nearest the object will shift, some moving just slightly, others swept along more dramatically. Gliese 710 is the heavy object, and the icy bodies of the Oort Cloud are the cubes. Its passage will generate a gravitational wave of influence, nudging countless bodies out of their orbits. The process works through tidal forces. Just as the Moon's gravity creates tides in Earth's oceans, a passing star exerts differential gravitational forces on objects across the Oort Cloud. Objects closer to Gliese 710 will feel a stronger pull than those farther away. This differential force slightly alters the orbits of comets, often converting previously stable trajectories into elongated paths that send them inward toward the Sun. Some objects may be ejected entirely from the solar system, while others will become potential long-period comets with orbital periods measured in millions of years. Simulations of stellar flybys show that even a star with a fraction of the Sun's mass can have significant effects when it passes through the inner Oort cloud. Gliese 710's mass, combined with its predicted proximity of 14,000 to 20,000 AU, makes it one of the most disruptive nearby stellar encounters in the next several million years. Its gravitational influence will propagate across a huge volume, subtly rearranging orbits, nudging comets toward paths that intersect with the inner planets. It's important to understand that this process will not be immediate. Comets that are perturbed by Gliese 710 will take tens of thousands to millions of years to travel from the outer solar system to the inner regions where planets like Earth reside. The star acts as a trigger, setting objects in motion, but the resulting comet showers will unfold over geological timescales. In other words, Gliese 710's gravitational disturbance will seed a future risk that humanity, or our descendants, will one day experience. The scale of the effect is mind-boggling. The Oort cloud may contain trillions of icy bodies, and even if only a fraction are sent on inward trajectories, that could translate into a significantly increased flux of long-period comets. Historically, these types of comets have had the potential to impact planets with catastrophic consequences. For Earth, such a surge in comets could mean more frequent large impacts, far exceeding the natural background rate of asteroid and comet collisions. To put the numbers into context, simulations of Gliese 710's flyby suggest that the star could send thousands of comets inward, over hundreds of thousands of years, creating a sustained period of elevated risk. The exact number depends on the star's closest approach, its mass, and the structure of the Oort cloud, which remains partially theoretical. But even with conservative estimates, the gravitational disturbance will be profound, effectively shaking the outer solar system and reshaping the long-term distribution of icy bodies. This is why astronomers emphasize that Gliese 710's danger does not come from the star itself. At tens of thousands of AU, it will pass far outside the planetary system. It won't collide with the Sun or Earth. Its threat is entirely gravitational, a subtle but potent force that will ripple across the frozen outskirts of our solar system. The star's mass and trajectory make it a natural catalyst for future cometary activity, a cosmic domino effect set in motion over millions of years. In essence, Gliese 710 is a cosmic stirrer, a gravitational agent awakening the long-dormant Oort cloud. Its passage will increase the number of comets sent toward the inner solar system, potentially creating a comet shower that could last for millennia. The disturbance will be gradual but inevitable, and it represents the clearest example we currently know of a star that can affect Earth not through fire or radiation, but purely through the invisible hand of gravity. When Gliese 710 passes through the inner Oort cloud, the gravitational disturbance it creates will not be just a momentary ripple. It will set off a chain reaction that could send a vast number of comets hurtling toward the inner solar system. These comets, some small and icy, others potentially massive, are the dormant relics of the solar system's formation, lying in wait for millions or even billions of years. Gliese 710 acts as a cosmic trigger, nudging these bodies out of stable orbits and sending them on elongated, highly elliptical paths that may eventually intersect with the planets, including Earth. The process begins in the outer solar system. The Oort cloud is a near-spherical shell of icy objects that extends from roughly 2,000 Australian dollars to over 100,000 Australian dollars. These objects are loosely bound to the Sun's gravity. As Gliese 710 approaches within 14,000 to 20,000 AU, its gravity will create tidal forces across the cloud, tugging more strongly on the nearest icy bodies and slightly altering the orbits of even more distant objects. While each individual tug is minor, the cumulative effect is significant. Over tens of thousands of years, some of these objects will be redirected onto trajectories that send them spiraling inward toward the inner solar system. Once nudged into these elongated orbits, the comets begin a slow but inevitable journey inward. Unlike asteroids, which mostly orbit in the flat plane of the solar system, these long-period comets come from all directions. Their highly inclined, often nearly random orbital paths make them especially dangerous, as they can approach the Sun and planets from angles where the typical planetary defenses, gravity wells of Jupiter and Saturn, are less effective at redirecting them. Simulations of Gliese 710's flyby predict that the result could be thousands of comets entering the inner solar system over a period of hundreds of thousands to millions of years. This would create a sustained period of heightened impact risk for Earth, Mars, Venus, and other planets. Unlike a single asteroid collision, this is a long-term cosmic event, more like a rainstorm of icy bodies, some of which could be large enough to cause catastrophic effects if they strike a planet. The scale of such a comet shower is difficult to exaggerate. Even a single large comet impact can have global consequences. The Chicxulub impactor, which struck Earth 66 million years ago and is linked to the extinction of the dinosaurs, was about 10 kilometers in diameter. Now imagine a scenario where dozens or hundreds of comets of various sizes enter the inner solar system over thousands of years. The cumulative risk rises dramatically. Some comets may collide with planets directly, while others could pass close enough to perturb planetary orbits, creating further gravitational chaos. Interestingly, not all comets triggered by Gliese 710 will hit the inner solar system immediately. Many will have orbits taking them out beyond the planets again, completing long-period elliptical orbits around the Sun. This means the effects of the star's flyby will ripple across millions of years, creating periods of elevated comet activity that could be spaced out over generations of solar system evolution. The timing and frequency of these comet showers depend on the specific interactions between Gliese 710 and the Oort Cloud, the distribution of icy bodies, and the subtle gravitational nudges they receive. Astronomers have studied these interactions using computer simulations. By modeling trillions of possible orbits in the Oort Cloud and applying Gliese 710's gravitational influence, they can estimate the likelihood and intensity of comet showers. These simulations suggest that Gliese 710 will create one of the most significant spikes in comet activity ever predicted, surpassing the minor fluctuations caused by other nearby stars. It's worth noting that comet showers are a natural part of solar system dynamics. Other stars occasionally pass near the Oort Cloud, and galactic tidal forces from the Milky Way itself constantly perturb these distant objects. However, Gliese 710's flyby is exceptional in both proximity and timing, making it the most significant stellar trigger for potential cometary activity in the next several million years. For Earth, the implications are both scientific and existential. On one hand, future astronomers, millions of years from now, may witness spectacular celestial displays, comets streaking across the sky from all directions, bright tails illuminated by the sun, a cosmic show unlike anything humans today could experience. On the other hand, this increased flux of long-period comets raises the risk of planetary impacts, some of which could have catastrophic consequences for life on Earth. In a cosmic sense, Gliese 710's flyby is like tossing a stone into a calm pond. The stone itself never touches the lily pads, planets, in the center, but the ripples spread across the water, jostling everything in their path. The comets are those ripples, initially distant and slow-moving, but over time capable of intersecting with the inner solar system and influencing its fate in dramatic ways. Ultimately, Gliese 710's flyby is a reminder of the interconnectedness of the universe. A star hundreds of trillions of kilometers away has the potential to indirectly influence the trajectory of comets that might one day strike our planet. Its approach will awaken the long-dormant icy bodies of the Oort Cloud, sending them inward as a natural consequence of gravity, a slow-motion celestial cascade that could last for millions of years. The true danger posed by Gliese 710's flyby lies not in the star itself, but in the comets it may send hurtling toward the inner solar system. Once Gliese 710 disturbs the Oort Cloud, a portion of these icy bodies will begin their long, elliptical journeys inward. While most may remain harmless, a fraction could cross paths with planets, including Earth. Understanding these impact risks requires examining both the mechanics of long-period comets and the scale of potential consequences. Long-period comets are unlike the near-Earth asteroids we frequently monitor today. They can approach from any direction, moving on highly inclined or even retrograde orbits, meaning they may intersect Earth's orbit at high speeds. Typical impact velocities for such comets can range from 50 km per second to over 70 km per second, far faster than most asteroid impacts. This speed, combined with their often enormous size, kilometers in diameter, means that even a single collision could release energy millions of times greater than the most powerful nuclear bombs. Consider the Chicxulub impactor, which struck Earth 66 million years ago. Roughly 10 to 15 kilometers in diameter, It released an estimated 100 million megatons of energy, triggering global wildfires, tsunamis, and climate collapse that contributed to the mass extinction of the dinosaurs. Long-period comets perturbed by Gliese 710 could be similar in size, or larger. If just a handful were to strike Earth, the consequences would be catastrophic, capable of reshaping ecosystems, wiping out species, and potentially threatening intelligent life. It is not just Earth at risk. All the inner planets, Mercury, Venus, Mars, and even the moons of the outer planets, could be impacted by these wandering icy bodies. While the probability of a single comet hitting a specific planet is low, the sheer number of comets set in motion increases the cumulative risk over tens of thousands of years. In other words, the flyby creates a long-term elevated threat, a subtle but persistent hazard embedded in the dynamics of the solar system. The unpredictability of long-period comets makes them particularly dangerous. Unlike near-Earth asteroids, which have relatively short orbital periods and can be tracked for decades or centuries, comets from the Oort Cloud may take millions of years to complete a single orbit. This means they could appear suddenly in the inner solar system, giving little warning and challenging any potential defenses. Current technology would struggle to deflect or mitigate impacts from such high-speed, massive bodies, especially if they arrive from a direction outside the plane of the planets. It's also worth noting that not all disturbances from Gliese 710 will result in direct impacts. Many comets may simply pass through the inner solar system, providing spectacular celestial displays while posing no immediate threat. However, even one large collision could trigger global consequences. Scientists therefore classify Gliese 710's flyby as a significant indirect hazard, not because it will strike us physically, but because it will increase the number of potentially dangerous objects in our neighborhood. Historical evidence underscores the seriousness of this threat. In addition to the Chicxulub impact, the Earth has endured numerous large impacts over its history. Craters like Tunguska in Siberia, 1908, while smaller, demonstrate that even relatively minor collisions can cause enormous local devastation. Long-period comets, however, carry energy orders of magnitude greater than Tunguska-level events, making them capable of global-scale effects. Gliese 710 essentially reshuffles the deck of the outer solar system. By perturbing the Oort Cloud, it introduces new comets onto potentially dangerous trajectories. While we cannot predict exactly which ones will intersect with Earth, the star's close approach significantly increases the likelihood of large-scale comet impacts over the subsequent hundreds of thousands of years. This is why astronomers consider it the most important predicted stellar encounter for the foreseeable future. The impact risk is probabilistic but real. Even a distant star, passing tens of thousands of AU away, can indirectly affect planetary safety by sending icy bodies inward. In the context of planetary defense, Gliese 710 reminds us that threats come not only from nearby asteroids but also from cosmic-scale interactions occurring far beyond the immediate reach of our telescopes. In summary, Gliese 710's greatest danger is not its physical presence but its ability to gravitationally disturb the Oort Cloud, sending long-period comets into the inner solar system. These comets could collide with Earth or other planets, potentially causing regional devastation or even global catastrophe, depending on their size and velocity. Over geological timescales, this encounter will elevate the frequency and intensity of cometary impacts, marking a subtle but profound chapter in the solar system's history. To understand the potential risks posed by Gliese 710, it helps to put the threat of comet impacts into a historical context. Earth has a long and often violent history of collisions with celestial objects, ranging from tiny meteorites to massive asteroids and comets capable of reshaping the biosphere. One of the most famous examples is the Chicxulub impact, which occurred approximately 66 million years ago. The Chicxulub impactor, likely around 10 to 15 kilometers in diameter, struck what is now the Yucatan Peninsula in Mexico. The consequences were catastrophic. The impact released an estimated 100 million megatons of energy, far exceeding the combined explosive power of all nuclear weapons ever built by humanity. It triggered massive wildfires, tsunamis, and a dramatic injection of dust and aerosols into the atmosphere, blocking sunlight and plunging the planet into a nuclear winter scenario. Global temperatures dropped, photosynthesis slowed, and ecosystems collapsed. The result was the mass extinction of roughly 75% of all species on Earth, including the dinosaurs. While the Chicxulub impactor was an asteroid, long-period comets from the Oort Cloud, like those potentially sent inward by Gliese 710, could produce similar or even more severe consequences. Comets tend to be more volatile than asteroids, composed of ices and rock, and often travel at higher velocities when entering the inner solar system. A comet of similar size to Chicxulub could strike with even greater kinetic energy due to its higher speed, magnifying the destructive potential. Earth's geological record shows multiple large impacts predating Chicxulub. Craters like Vredefort in South Africa, Sudbury in Canada, and Popogai in Russia bear witness to collisions that reshaped continents, caused mass extinctions, or at least triggered significant environmental upheavals. Many of these impacts were caused by asteroids, but comets, especially those on long-period orbits, have also likely played a role. Unlike near-Earth asteroids, comets can come from any direction, increasing the unpredictability of potential impacts. The history of cometary impacts underscores a crucial point: the solar system is not a static environment. Even though we often perceive space as calm and unchanging, it is dynamic and full of hazards. Gliese 710's future flyby is part of this dynamic picture. By disturbing the Oort Cloud, it has the potential to initiate a series of cometary events analogous to some of the catastrophic collisions in Earth's deep past. While these effects won't occur immediately, comets may take thousands or hundreds of thousands of years to reach the inner planets. The historical record shows that such impacts have the potential to radically alter life on Earth. It is also interesting to note that previous mass extinctions or significant environmental shifts on Earth may have been influenced by cosmic events. While the Chicxulub impact is the most famous, paleontologists and astronomers have identified other periods in Earth's history with increased impact rates, possibly due to stellar encounters or perturbations of the Oort Cloud. This strengthens the relevance of studying Gliese 710 today. It's not just a theoretical curiosity but a real factor in understanding the long-term dynamics of Earth's environment and the solar system. In essence, the historical record of comet and asteroid impacts serves as both a warning and a guide. The Chicxulub impact demonstrates the devastating potential of a single celestial collision, and Gliese 710 illustrates how external forces can increase the likelihood of such events in the distant future. It reminds us that even though we are safe today, the universe is full of mechanisms, like gravitational disturbances from passing stars, that can dramatically alter the course of planetary history over millions of years. By looking back at Earth's past impacts, we gain perspective on what may happen millions of years from now. Gliese 710 won't hit the Earth directly, but it could trigger a cascade of cometary events with historical precedent for devastation. This historical lens makes the abstract danger far more tangible. The same forces that once wiped out the dinosaurs could, in a different form, be activated again by a star passing through the Oort Cloud. The predictions about Gliese 710's flyby might sound like science fiction, but they are the result of decades of meticulous astronomical measurement and analysis. Astronomers are able to calculate the star's path with an extraordinary degree of certainty using precise observations of its motion, position, and velocity, combined with sophisticated models of the Milky Way's gravitational environment. This is why scientists can state, with confidence, that Gliese 710 will pass within 14,000 to 20,000 AU of the Sun in roughly 1.3 million years. The first step in determining a star's trajectory is measuring its proper motion, its movement across the sky relative to distant background stars. Proper motion gives astronomers the two-dimensional component of the star's motion, showing how it drifts along the celestial sphere. But proper motion alone is not enough. To fully understand a star's path in 3 dimensions, astronomers also need its radial velocity, how fast it is moving toward or away from us. By combining proper motion with radial velocity, astronomers can reconstruct the star's 3-dimensional velocity vector in space. Gliese 710 has been observed for decades using both ground-based telescopes and space-based instruments, allowing scientists to track its motion with high precision. The star's proper motion is small but measurable, reflecting its slow but steady drift through the galaxy relative to the Sun. Its radial velocity has been determined through spectroscopic observations, which measure the Doppler shift of light emitted by the star. A shift toward the blue end of the spectrum indicates the star is approaching, while a red shift indicates it is moving away. Gliese 710 exhibits a slight blue shift, confirming that it is indeed moving toward the solar system. Once the velocity is known, astronomers use gravitational models of the Milky Way to predict the star's future trajectory. The galaxy's mass is not evenly distributed. Stars, dark matter, gas clouds, and the galactic center all exert gravitational forces that curve a star's path over time. Sophisticated computer simulations account for these forces, integrating Gliese 710's motion over millions of years to determine its closest approach to the Sun. These models also account for uncertainties in initial measurements, generating a range of possible trajectories to estimate the margin of error for the flyby distance. The precision of these predictions has been dramatically enhanced by the European Space Agency's Gaia mission, which has measured the positions, parallaxes, and proper motions of over 1 billion stars in the Milky Way. Gaia's instruments can detect motions as small as microarcseconds per year, equivalent to observing the width of a human hair from thousands of kilometers away. For Gliese 710, Gaia's data has refined previous estimates, narrowing the predicted closest approach to a relatively tight range of 14,000 to 20,000 AU. This level of precision is unprecedented and allows astronomers to model the potential effects on the Oort cloud with confidence. It's also worth noting that these calculations are probabilistic rather than absolute. Tiny uncertainties in measurements can accumulate over millions of years. However, even when accounting for all sources of error, including potential gravitational influences from unknown objects, the flyby remains virtually certain to occur. Gliese 710 is the closest predicted stellar encounter with the solar system in the next several million years, and the odds of it missing the inner Oort cloud entirely are extremely low. Astronomers also cross-check their predictions by modeling the interactions of other nearby stars, comparing historical data, and simulating different gravitational scenarios. The consistency across multiple datasets and simulation methods reinforces the reliability of the predictions. In other words, this is not speculation based on incomplete data. It is the result of rigorous, peer-reviewed scientific analysis grounded in precise measurements and computational modeling. The confidence in Gliese 710's trajectory is significant for several reasons. It allows scientists to predict not just the star's position in space but also its long-term effects on the solar system, particularly the Oort cloud. By knowing when and how the star will pass, researchers can model the resulting comet showers, assess potential impact risks for Earth, and understand the broader dynamics of our solar system's outermost regions. Without this level of certainty, discussions of cometary hazards and gravitational disturbances would remain largely theoretical. In short, Gliese 710's flyby exemplifies the power of modern astronomy. By precisely measuring the motion of a distant star today, we can predict its influence on the solar system over 1 million years in the future. It highlights the extraordinary accuracy achievable when advanced telescopes, spectroscopic analysis, and space-based missions like Gaia are combined with sophisticated gravitational modeling. This isn't just prediction, it's a high-confidence forecast of a cosmic event that will unfold long after human civilization as we know it may have evolved or disappeared. The Gaia mission, launched by the European Space Agency, ESA, in 2013, has revolutionized our understanding of the Milky Way and, in particular, made the precise prediction of Gliese 710's flyby possible. Gaia is a space observatory designed to map the positions, distances, and motions of over 1 billion stars in the galaxy with unprecedented precision. Its mission is to create the most detailed three-dimensional map of the Milky Way ever produced, revealing the structure, dynamics, and evolution of our galactic neighborhood. Gaia accomplishes this through a combination of astrometry, photometry, and spectroscopy. Astrometry involves measuring the positions and movements of stars with extreme accuracy, allowing scientists to track proper motions across the sky. Photometry measures the brightness of stars, which helps determine properties such as luminosity and temperature. Spectroscopy analyzes the light emitted or absorbed by stars to measure their radial velocities, how fast they are moving toward or away from us. Combining all three techniques gives astronomers a complete picture of a star's position, motion, and physical characteristics. For Gliese 710, Gaia's contribution has been game-changing. Before Gaia, astronomers could estimate the star's proper motion and radial velocity, but uncertainties were significant. Predictions of its closest approach to the solar system varied widely, leaving room for doubt about whether it would even pass close enough to affect the Oort cloud. Gaia's high-precision measurements have dramatically reduced these uncertainties, allowing scientists to pinpoint the star's trajectory with a level of accuracy previously unimaginable. Gaia measures positions with precision down to microarcseconds, which is equivalent to detecting the width of a human hair from thousands of kilometers away. It also measures parallaxes, which provide direct distance measurements to stars, and proper motions, which track how stars shift across the sky over time. By combining these measurements, Gaia enables astronomers to calculate three-dimensional velocity vectors for stars like Gliese 710, making it possible to simulate their motion millions of years into the future. The data from Gaia have confirmed that Gliese 710 is indeed on a direct approach toward the solar system. Its radial velocity indicates that it is moving toward us, while its proper motion aligns with the predicted trajectory that will take it through the inner Oort cloud in roughly 1.3 million years. This allows scientists not only to forecast its closest approach distance, 14,000 to 20,000 AU, but also to model its gravitational influence on the Oort cloud with high fidelity. One of the remarkable aspects of Gaia's work is the ability to quantify uncertainty. Even over millions of years, tiny errors in measurement can propagate, so astronomers use Gaia's data to generate probabilistic models of Gliese 710's flyby. These simulations produce a range of possible distances and impact scenarios for the Oort cloud, giving a realistic picture of the likelihood and intensity of future comet showers. Despite the uncertainties, all models converge on the conclusion that Gliese 710 will be the closest and most influential stellar encounter for our solar system in the near cosmic future. Gaia has also provided insights into other nearby stars, but Gliese 710 stands out because of the combination of its approach distance, mass, and trajectory. Many stars pass hundreds of thousands of AU from the Sun, posing no significant threat. Gliese 710, however, will pass deep within the Oort cloud, making it a unique case study in stellar encounters and their potential consequences for the inner solar system. Beyond Gliese 710, Gaia's broader mission is reshaping our understanding of the Milky Way. It is helping astronomers identify past and future close stellar encounters, map the distribution of dark matter, and trace the formation history of our galaxy. The precision and scale of Gaia's data are unprecedented, and its contributions continue to improve our ability to predict cosmic events on timescales of millions of years. In short, without Gaia, our knowledge of Gliese 710's trajectory would be far less certain. This spacecraft has provided the definitive measurements that allow scientists to assert, with confidence, that this orange dwarf star will pass close enough to the solar system to disturb the Oort cloud and potentially send a new generation of long-period comets toward the inner planets. Gaia exemplifies the power of modern astronomy, observing stars with incredible precision today to understand their influence on the solar system millions of years into the future. While Gliese 710 is undoubtedly the star generating the most concern for astronomers regarding future gravitational disturbances, it is important to remember that it is not alone in passing near the solar system. Stars move through the Milky Way at varying velocities and along diverse trajectories. Occasionally, these motions bring them relatively close to our Sun, resulting in stellar flybys. These encounters happen on cosmic timescales, sometimes millions of years apart, and vary greatly in distance and effect. Many nearby stars have passed or will pass at distances ranging from tens of thousands to hundreds of thousands of AU. For instance, Scholz's star, a binary system, passed within about 52,000 Australian dollars of the Sun approximately 70,000 years ago. While this flyby was relatively close, it was still far enough from the inner Oort cloud that its gravitational effect on the solar system was modest. Other stars, like HIP 85605, have been proposed as potential future visitors, but the predictions are less certain, and the projected distances are generally much larger than Gliese 710's. What makes Gliese 710 exceptional is the combination of proximity, mass, and trajectory. At 14,000 to 20,000 AU, it will pass much closer than any other known star in the next several million years. Its mass, about 60% of the Sun's, is enough to produce significant gravitational effects on the Oort cloud, unlike smaller, more distant stars whose influence is negligible. This makes it the most important predicted stellar encounter in terms of potential cometary activity in the inner solar system. It's also noteworthy that while stars frequently pass near the solar system on galactic scales, the vast majority remain too distant to have any meaningful effect. The Sun is embedded in a relatively sparse neighborhood of the Milky Way, so close encounters are rare. A flyby like Gliese 710's, deep into the Oort cloud, is extraordinary and allows astronomers to study the potential consequences of such rare events with unprecedented detail. In essence, while stellar flybys are not unusual, Gliese 710 is remarkable for being the closest and most impactful star we currently know will approach the solar system. Its path offers a unique opportunity to understand how external forces can disturb the solar system's outermost regions and potentially set off a long-term cascade of comets into the inner planets. The distinction is critical. Stars pass near us relatively frequently on cosmic timescales, but Gliese 710 is predicted to penetrate the inner Oort Cloud, a region few other stars are projected to reach. This makes it not just another passing star but a cosmic event of rare significance, a gravitational influence that could leave a lasting imprint on the solar system over millions of years. Gliese 710 matters because, in terms of future stellar encounters, it represents an unprecedented event for the solar system in the foreseeable cosmic future. While other stars pass near the Sun, most do so at distances too great to significantly affect the planets or even the outer icy boundaries of our system. Gliese 710, in contrast, is projected to pass deep into the inner Oort Cloud, potentially triggering a cascade of cometary activity that could reach the inner solar system. This combination of proximity, mass, and trajectory makes it the most significant predicted stellar encounter in the next several million years. The reason this matters is not that the star itself will collide with Earth or the Sun, that will not happen, but because of the indirect consequences. Gliese 710's gravitational pull will disturb trillions of icy bodies in the Oort Cloud, nudging a subset onto trajectories that could intersect with the orbits of the planets. This makes the star a major factor in the long-term evolution of the solar system, influencing the distribution of comets and potentially increasing the frequency of impacts on planets, including Earth. Such an event is unique in our current understanding because the scale of disruption is far greater than other known nearby flybys. To appreciate why Gliese 710 is so consequential, it helps to put the encounter in cosmic context. Most stars pass hundreds of thousands of AU from the Sun, which is essentially a safe distance for the solar system. The Oort Cloud acts as a buffer, protecting the inner planets from minor gravitational nudges. Gliese 710, however, will penetrate that buffer zone, reaching the inner portions of the cloud at roughly 14,000 to 20,000 AU. This proximity is so rare that astronomers consider it a once-in-several-million-years event, making it the most significant potential gravitational disturbance of our planetary neighborhood in that time frame. The implications are both scientific and existential. From a scientific perspective, Gliese 710's approach is an extraordinary opportunity to study the dynamics of stellar flybys and their effects on distant icy bodies. By modeling its trajectory and the subsequent behavior of the Oort Cloud, astronomers can improve our understanding of how stellar interactions shape planetary systems over millions of years. This has broader relevance beyond our solar system, offering insights into how similar flybys might influence exoplanetary systems elsewhere in the galaxy. From a planetary safety perspective, Gliese 710 highlights a type of risk that is fundamentally different from everyday threats. Unlike asteroids or comets already in the inner solar system, which we can monitor and potentially mitigate, this is a long-term cosmic risk. Its effects will unfold over hundreds of thousands to millions of years, meaning it represents a slow-motion hazard that will gradually increase the probability of comet impacts. For planetary defense planning, even in the far future, understanding such encounters is essential. Furthermore, the encounter underscores the fragility of the solar system's outer reaches. While the planets are relatively safe from direct stellar collisions, the Oort Cloud exists in a delicate balance, held in place by the Sun's gravitational pull yet susceptible to perturbations from passing stars. Gliese 710 serves as a vivid reminder that our solar system is not isolated but part of a dynamic galactic environment where nearby stars can influence its structure, even from tens of thousands of AU away. In summary, Gliese 710 matters because it is the closest predicted star to approach the solar system in millions of years, passing deep into the Oort Cloud, and because it will have lasting consequences on the distribution of comets. Its significance lies not in immediate danger but in its capacity to reshape the outer solar system, increase the likelihood of cometary impacts, and provide a rare, observable example of stellar gravitational influence in action. This event gives astronomers an unprecedented chance to study long-term solar system dynamics and reminds us that even distant stars can have profound effects on our cosmic neighborhood. When dealing with predictions that span millions of years into the future, it's natural to ask, could Gliese 710 pass even closer than currently predicted? The short answer is, while astronomers have extremely precise measurements, there is always a margin of uncertainty in such long-term forecasts. Even tiny errors in distance, velocity, or galactic gravitational modeling can compound over a million years, slightly altering the predicted closest approach. The primary source of uncertainty comes from the limitations of measuring a star's position and motion today. Even with ESA's Gaia spacecraft, which provides micro-arcsecond precision, there are still small observational errors. Proper motion measurements, parallax determinations, used to calculate distance, and radial velocity measurements all carry tiny uncertainties. Over 1.3 million years, these seemingly insignificant errors can shift the predicted path slightly, meaning that Gliese 710 could pass a bit closer, or a bit farther, than the current estimate of 14,000 to 20,000 AU. Another factor is the gravitational influence of the Milky Way. The Sun, Gliese 710, and other nearby stars all orbit the galactic center, and they are influenced by the galaxy's mass distribution, including stars, gas clouds, and dark matter. While astronomers model these forces with remarkable accuracy, our knowledge of every minor gravitational influence is incomplete. Over long timescales, small deviations in galactic tides or passing stars could slightly alter Gliese 710's trajectory, nudging it closer, or slightly farther, than predicted. In addition, the interaction with other stars or unseen objects in the vicinity could modify the star's path. Although the neighborhood around the Sun is relatively sparse, there are countless faint stars and substellar objects, brown dwarfs, rogue planets, and possibly unseen massive bodies, that could exert minor gravitational tugs on Gliese 710 during its journey. Even minor deflections accumulate over time, contributing to the range of possible closest approach distances. However, despite these uncertainties, astronomers are confident that any variation is unlikely to change the overall conclusion. Gliese 710 will pass within the inner Oort cloud. Current models, incorporating Gaia's data and sophisticated simulations of galactic dynamics, indicate that even with margins of error, the star will penetrate far enough to disturb the Oort cloud significantly. In other words, while the exact distance may vary by a few thousand AU, the general risk of a cometary surge remains firmly supported by the data. The margin of error is also quantified in studies. For example, simulations using probabilistic methods generate a range of possible flyby distances, usually expressed as a confidence interval. Even at the outer edge of this range, Gliese 710's closest approach remains closer than almost all other stars expected to pass near the solar system in the next several million years. In this sense, the "could it get closer?" question is already baked into the models, and astronomers conclude that any variation is unlikely to significantly change the star's potential to perturb the Oort cloud. It's also important to note that even if Gliese 710 were to pass slightly closer than predicted, the star itself would still remain far outside the planetary system. There is no scenario in which it would collide with the Sun or planets. The variation in distance only affects the number of Oort cloud objects perturbed and, consequently, the intensity of the resulting comet showers. A closer pass could increase the number of comets sent toward the inner solar system, but the overall picture, a gravitational disturbance leading to long-term cometary activity, remains unchanged. In essence, astronomers acknowledge that predictions spanning millions of years carry small uncertainties, and Gliese 710's closest approach could shift slightly due to observational errors, galactic tides, or gravitational influences from other stars. However, the broad outcome is secure. It will pass through the inner Oort cloud, creating the most significant predicted stellar perturbation of our solar system in the near cosmic future. Any small variations in distance serve to refine estimates of comet flux but do not change the underlying story of Gliese 710 as a major future influencer of our outer solar system. Despite the dramatic predictions surrounding Gliese 710, one thing is absolutely certain. The star itself will not collide with Earth, the Sun, or any of the planets in our solar system. The idea of a star smashing directly into the Sun might sound like a scene from a sci-fi movie, but the actual physics of the flyby are far less sensational, though still profoundly important in a more subtle way. Gliese 710's predicted trajectory places it at a closest approach of roughly 14,000 to 20,000 AU, or about 0.06 to 0.08 light-years from the Sun. To put that in perspective, the distance between Earth and the Sun is $1, so even at its nearest, Gliese 710 will be tens of thousands of times farther away than the planets. In other words, it will pass far outside the orbits of all known planets, including Pluto at roughly $40. There is simply no physical possibility for a direct collision with the Sun or any planet in our solar system. Astronomers are able to predict this with high confidence thanks to precise measurements of the star's position, velocity, and trajectory, primarily from ESA's Gaia mission. These data allow scientists to model the star's path millions of years into the future with remarkable accuracy. Even when accounting for small uncertainties in distance, velocity, and galactic gravitational influences, the closest approach always remains well outside the planetary region. The missed distance is enormous on a human scale, and there is essentially zero risk of Gliese 710 striking the Sun or Earth. It's also worth noting that stellar collisions with the Sun are extraordinarily rare. Stars are incredibly far apart, even in relatively dense regions of the galaxy. The vastness of space makes direct collisions almost impossible. Gliese 710's flyby is remarkable not because it might hit us, but because it will pass close enough to influence the outer solar system gravitationally. The danger comes not from the star's physical presence but from the ripple effect it creates in the Oort Cloud, sending comets inward over long timescales. To visualize this, imagine the solar system as a small marble in the center of a giant stadium, and the Oort Cloud as a massive sphere of dust surrounding it. Gliese 710 is like a larger marble rolling through the outer edges of the stadium. It never touches the small marble at the center, but it can stir the dust around it, causing particles to move toward the center over time. That dust represents the icy bodies in the Oort Cloud, which could be redirected toward the planets, including Earth. The star's role is purely gravitational, not collisional. Even for the planets most distant from the Sun, like Neptune or Pluto, the closest approach of Gliese 710 is more than 300 times the distance to Pluto. No gravitational slingshot or direct collision is possible at this range. While its gravity will certainly influence the loosely bound icy bodies in the Oort Cloud, the planets themselves are firmly anchored by the Sun's much stronger local gravitational pull. The inner and outer planetary systems are safely insulated from any direct encounter. In short, there is no need for alarm regarding a direct impact. Gliese 710 will sweep past the solar system harmlessly in terms of collision, and the planets will continue on their orbits undisturbed. The real significance of the star lies in its ability to stir up the distant Oort Cloud, potentially sending long-period comets toward the inner solar system over hundreds of thousands of years. That is the subtle, indirect danger, not a fiery crash of a star into our Sun. The reassurance here is straightforward. Even though Gliese 710 will be the closest known stellar approach in millions of years, it will not physically hit us. The star's distance is immense in planetary terms, and the direct risk to Earth is effectively zero. Our attention should instead focus on the secondary effects, such as the gravitational perturbations of the Oort Cloud that could increase cometary activity in the distant future. While Gliese 710 itself poses no direct threat to Earth or the planets, the real danger lies in what the star does to the Oort Cloud, and how that disturbance could eventually send comets hurtling toward the inner solar system. Understanding this distinction is crucial for grasping why astronomers describe Gliese 710 as a significant threat, even though it will never collide with the Sun or planets. The Oort Cloud is a vast, loosely bound shell of icy bodies extending tens of thousands of AU from the Sun. These objects are only weakly held by solar gravity, meaning that even modest gravitational influences from a nearby star can perturb their orbits. Gliese 710's mass, trajectory, and proximity make it uniquely capable of disturbing this distant region. When it passes through the inner Oort Cloud, its gravity will tug on countless icy bodies, nudging them out of stable, nearly circular orbits into elongated, highly eccentric trajectories. These perturbed objects may then begin their long inward journeys toward the Sun, sometimes taking hundreds of thousands or even millions of years to reach the inner solar system. Unlike the star itself, which passes quickly and leaves the planetary orbits intact, these comets will follow paths that intersect with the orbits of planets, including Earth. Over time, the result is a heightened risk of collisions, which is the true source of danger from Gliese 710. It is important to note that the risk is indirect and probabilistic, not immediate. Gliese 710 does not shoot comets at Earth. Instead, it acts as a gravitational catalyst, disturbing a region of space filled with potential impactors. The comet's eventual arrival in the inner solar system depends on the dynamics of their new orbits, solar gravity, and interactions with other bodies like Jupiter and Saturn. Even a small fraction of perturbed comets could dramatically increase the frequency of long-period comet appearances over geological timescales, some of which may cross Earth's orbit. To visualize this, imagine a calm pond with floating icebergs. Gliese 710 is like a boat moving near the edge. It doesn't crash into the icebergs, but its wake sends many of them drifting toward the center of the pond. The center represents the inner solar system, and the icebergs represent Oort Cloud comets. While the star itself passes harmlessly, its gravitational wake sets in motion a long-term risk that unfolds slowly over thousands of years. This distinction also clarifies why scientists are so focused on monitoring and modeling Gliese 710's flyby. The danger is not immediate, and no human lifetime will witness a direct threat from the star. But for future civilizations, or even the distant evolutionary trajectory of Earth's biosphere, these gravitational perturbations could trigger comet showers, with potentially catastrophic consequences. In essence, Gliese 710 is a slow-motion agent of change. It reshapes the solar system's outer boundary and seeds the conditions for future cometary impacts. Moreover, this highlights the broader principle in planetary defense. Most threats come from indirect processes, not direct collisions. Near-Earth asteroids are relatively easy to monitor because their orbits are well known and their travel times short. Long-period comets, especially those perturbed by distant stars like Gliese 710, are far harder to anticipate because their journeys are measured in millions of years. Understanding stellar flybys allows scientists to predict long-term trends in impact risk, even if no immediate action is possible. In summary, the real threat from Gliese 710 is the cometary domino effect it sets off in the Oort Cloud. The star itself will remain harmlessly distant, passing well outside the planetary region. But its gravitational influence will disturb icy bodies, increasing the likelihood of long-period comets entering the inner solar system over hundreds of thousands of years. This distinction, between the star itself and its gravitational consequences, is critical for appreciating why Gliese 710 is considered the biggest known stellar threat to Earth. When Gliese 710 finally reaches its closest approach to the solar system, it won't just be a distant point on a telescope image. It will become a remarkably bright object in the night sky, potentially visible to the naked eye. While the star itself won't impact Earth directly, its apparent brightness will increase dramatically as its distance shrinks from today's 63 light-years to just 0.06 to 0.08 light-years at closest approach. To grasp the scale of this change, we can examine the relationship between distance, luminosity, and apparent magnitude. Currently, Gliese 710 is a faint star, barely noticeable even with powerful telescopes. Its luminosity is about 16% that of the Sun, typical for a K-type orange dwarf. At its present distance of 63 light-years, roughly 19,400 parsecs, this low luminosity makes it invisible to the naked eye from Earth. However, as it approaches the solar system, the inverse square law of light tells us that brightness increases dramatically as the distance decreases. Simply put, if the distance to a light source is cut in half, its apparent brightness grows by a factor of 4. Reducing the distance from tens of light-years to just 0.06 to 0.08 light-years represents a change in distance by a factor of roughly 800 to 1000, which translates to an enormous increase in apparent brightness. Estimates suggest that at its closest approach, Gliese 710 could shine with an apparent magnitude of around -2 to -3, making it brighter than Sirius, the brightest star in today's night sky. Unlike Sirius, which glimmers in the winter sky, Gliese 710 would appear as a steady, prominent orange star, dominating the night sky for thousands of years during its slow passage through the inner Oort Cloud. Its distinctive orange hue, typical of K-type dwarfs, would make it unmistakable against the backdrop of familiar stars, providing a cosmic spectacle unlike anything humans currently experience. This brightness would not be a fleeting moment. The star's motion relative to the solar system is slow on human timescales, so Gliese 710 would remain a prominent fixture in the sky for millennia, gradually moving against the background stars. For future civilizations, or distant descendants of humanity, its approach could serve as a celestial landmark, a visual reminder of the ongoing dynamics of the galaxy. It would also provide astronomers with an unprecedented opportunity to study a star at such close proximity, including its spectral characteristics, magnetic activity, and possibly even its influence on surrounding space debris in real time. The sky would literally be reshaped by Gliese 710. Constellations as we know them would be temporarily distorted by its brightness and position. Imagine familiar star patterns suddenly overshadowed by a bold orange star dominating the night sky. For stargazers, astronomers, and anyone with even modest observational tools, Gliese 710 would be impossible to ignore, a vivid example of the dynamic and ever-changing universe we inhabit. Interestingly, While Gliese 710's brightness will make it a spectacular visual feature, it won't generate dangerous radiation for Earth. Its output is far less than the Sun's, and its distance, even at closest approach, is still vast enough that planetary atmospheres and magnetic fields would remain unaffected. The star's dramatic presence in the sky would be purely aesthetic and scientific, a cosmic show rather than a hazard in itself. In summary, Gliese 710 promises to be a truly extraordinary sight. For anyone living at the time of its approach, the night sky would feature a bright, prominent orange star, outshining familiar stars and creating a rare opportunity for observation. It would serve as a natural celestial marker for a period of significant cosmic activity, as the star's gravitational influence quietly stirs the distant Oort Cloud. The spectacle in the sky would be a reminder that even though the star itself is harmless to Earth, its presence signals the beginning of a long-term gravitational ripple that could reshape the solar system over the following hundreds of thousands of years. Gliese 710's flyby represents not only a potential gravitational threat but also an extraordinary astronomical opportunity. Close stellar encounters of this magnitude are exceedingly rare, and observing one from such proximity would provide future astronomers with insights that are otherwise impossible to obtain. For millennia, scientists will have a living laboratory to study the detailed physics of a nearby star and its effects on the surrounding space environment. From an observational standpoint, the close approach offers multiple avenues for discovery. Today, astronomers must rely on distant stars that appear as tiny points of light, often hundreds or thousands of light-years away. But when a star like Gliese 710 passes just 14,000 to 20,000 AU from the Sun, it will be close enough to study with unparalleled clarity. Instruments of the future could measure its surface temperature, magnetic field, rotation rate, stellar flares, and even small-scale surface features with far greater precision than is currently possible for any star outside the solar system. For example, star spots or other activity on its surface could be directly observed, offering a glimpse into stellar behavior that is typically inferred only indirectly. The flyby also provides a rare chance to study the interactions between a passing star and a planetary system. As Gliese 710 moves through the inner Oort Cloud, astronomers could observe, in real time, how its gravity perturbs icy bodies on the edges of the solar system. This would allow researchers to test and refine models of stellar flybys, comet dynamics, and long-period orbital evolution. It would be the first opportunity in human history to witness a major Oort Cloud disturbance as it unfolds, providing data to improve predictions of comet showers and better understand the long-term evolution of planetary systems. Moreover, the flyby could serve as a natural experiment in gravitational physics. While Newtonian gravity accurately predicts the broad motions of stars and comets, the event could help test more subtle effects, such as gravitational interactions over enormous distances and the influence of galactic tides. Advanced sensors of the future might even detect minute changes in the solar system's outer reaches caused by Gliese 710's passage, providing insights into the dynamics of loosely bound objects in extreme environments. This is an astronomical opportunity unlike any other because stars rarely come close enough for such direct, detailed observation. Even historically close encounters, like Scholz's star 70,000 years ago, passed too far away for any direct measurements to be taken. We can only infer their past trajectories from indirect evidence. Gliese 710 will be visible, measurable, and trackable, allowing future astronomers to gather real-time data on the star itself, its trajectory, and its effects on the solar system. In addition to scientific studies, the flyby could inspire technological and exploratory advancements. Future civilizations might develop space probes or telescopic networks to monitor Gliese 710 and its perturbations in the Oort Cloud, allowing humanity, or its descendants, to observe a rare cosmic event on a timescale accessible to intelligent observers. Such monitoring could also serve a practical purpose, tracking comets nudged toward the inner solar system and potentially mitigating impact risks. Finally, from an educational and philosophical perspective, the flyby underscores the dynamic nature of the galaxy. Unlike the fixed star patterns we see in the night sky today, Gliese 710 will dramatically alter the local stellar landscape. Observers will witness firsthand how the Milky Way is not static but filled with stars moving in complex orbits, occasionally coming close enough to influence one another gravitationally. This will be a rare chance to see cosmic mechanics in action, bringing the abstract principles of astronomy into vivid, observable reality. In essence, Gliese 710's approach is a once-in-millions-of-years opportunity. It offers a unique combination of proximity, predictability, and observable effects, providing a natural laboratory for studying stellar behavior, gravitational interactions, and the long-term dynamics of the solar system. It is not just a potential threat, it is also a remarkable chance for scientific discovery, giving future astronomers insights that could refine our understanding of stellar flybys, comet dynamics, and the subtle forces shaping planetary systems across the galaxy. To truly grasp the magnitude of Gliese 710's predicted flyby, it's essential to consider the cosmic timescale on which it occurs. The star will reach its closest approach in approximately 1.3 million years, an almost incomprehensibly long period when compared to the span of human history. To put this into perspective, consider that Homo sapiens have existed for roughly 300,000 years, meaning that Gliese 710 will not arrive until over 4 times the age of our species from its first emergence. Even modern civilization, which has existed for about 10,000 years, represents less than 1% of the time until this stellar encounter. When we look at history, the oldest known civilizations, the Sumerians, Egyptians, and Indus Valley societies, emerged just a few thousand years ago. If Gliese 710 were to arrive tomorrow on a human timescale, we would be discussing a star flyby occurring long before recorded history began, yet extending far beyond the existence of any technological institutions. This perspective highlights just how fleeting humanity is in the cosmic timeline, and how even dramatic astronomical events like Gliese 710's approach unfold on a scale that dwarfs our comprehension. From a geological perspective, 1.3 million years is still a relatively short interval, but it is enough for substantial changes to occur on Earth. For instance, during the Pleistocene epoch, which began around 2.6 million years ago, the planet experienced cycles of ice ages, massive shifts in climate, and the rise and extinction of numerous species, including mammoths and saber-toothed cats. By the time Gliese 710 arrives, Earth's continents may look different. Sea levels could have changed dramatically, and the biosphere could be vastly altered. It's likely that humans, or our descendants, will have evolved or adapted to environments that are difficult for us to imagine today. This long timescale also underscores why the flyby is both a distant and yet scientifically important event. While it will not affect humanity directly in any immediate way, it is still possible to model its consequences because celestial mechanics operate predictably over millions of years. Stars, comets, and planetary orbits move according to well-understood gravitational laws, allowing astronomers to forecast the trajectory of Gliese 710 and its influence on the Oort Cloud despite the enormous timescale. Unlike human history, which is shaped by unpredictable events, the physics governing stellar flybys is extraordinarily reliable over millions of years. Another way to appreciate the cosmic timescale is by considering other astronomical events. For instance, the last time a star passed relatively close to the Sun was Scholz's star, about 70,000 years ago, tiny in comparison to 1.3 million years. The next notable close encounter after Gliese 710 may not occur for millions of years more. Gliese 710 thus represents a rarely occurring celestial event on the cosmic calendar, a moment when the solar system will experience a gravitational visitor in its outermost reaches. The cosmic timescale also reminds us that while humans may be fascinated, or alarmed, by Gliese 710, this star has no concept of urgency. Its journey through the Milky Way spans millions of years, moving slowly in relation to our fleeting human lifetimes. The star's gravitational influence will also unfold gradually. As it perturbs the Oort Cloud, comets will take tens of thousands to millions of years to reach the inner solar system. Even the most dramatic effects, like potential comet showers, will be spread over a geological timescale that far exceeds the lifespan of any civilization we currently know. In a sense, the 1.3 million year horizon emphasizes our relative smallness and transience. Gliese 710 is a reminder that the universe operates on timescales that dwarf human experience. Yet, despite this, we can predict its path, anticipate its effects, and study its consequences, demonstrating the power of scientific reasoning to bridge the gap between human perception and cosmic events. The flyby becomes not just an astronomical curiosity, but a window into the slow-motion dynamics that govern our galaxy, where stars, comets, and planets interact over millions of years, quietly shaping the structure of the solar system. When we consider Gliese 710's flyby, one of the most profound questions is, will humans, or our descendants, still be around to witness its approach? With a timeline of approximately 1.3 million years, This event exists far beyond the span of modern civilization. To put this in context, the entirety of recorded history, spanning roughly 5,000 to 6,000 years, is just 0.5% of the time until the flyby. Even Homo sapiens, who have been around for about 300,000 years, represent only a fraction of the interval before Gliese 710 reaches its closest point. On a purely biological scale, species rarely persist unchanged for such long periods. For example, the average lifespan of mammalian species is often measured in hundreds of thousands of years, meaning that humans as we know them may evolve significantly, or even be replaced by descendants better adapted to future environments, by the time Gliese 710 arrives. Environmental changes, climate shifts, and geological events could alter the planet in ways that favor species quite different from ourselves. On a technological and societal scale, predicting human survival for 1.3 million years is nearly impossible. Civilizations rise and fall on timescales of hundreds to thousands of years. Technological systems evolve rapidly, and global catastrophes can radically alter trajectories. Yet, if humanity or its successors manage to sustain intelligent life over geological timescales, the flyby of Gliese 710 could become a phenomenon that is observed, studied, and potentially even prepared for. From a planetary defense perspective, the cometary disturbances triggered by Gliese 710 represent a hazard that unfolds gradually over tens of thousands to hundreds of thousands of years. This extended timeline could allow highly advanced civilizations to anticipate, monitor, and mitigate cometary threats long before they intersect the inner solar system. Future humans, or post-human civilizations, might have technologies far beyond anything we currently possess, enabling the detection of incoming comets early and providing options to divert or destroy potential impactors. However, the survival of humanity in the face of such distant events is intertwined with more immediate challenges. Global issues such as climate change, resource depletion, and nuclear or ecological disasters operate on much shorter timescales and could threaten our long-term persistence. If civilizations can navigate these shorter-term threats successfully, it increases the likelihood that intelligent observers will still be present to witness Gliese 710's arrival. In other words, our ability to survive and thrive in the near term may directly determine whether we are present for this rare cosmic event. It is also worth noting that even if humans, or a recognizable civilization, no longer exist, Gliese 710 will still approach according to the precise mechanics of celestial motion. The star and the Oort Cloud will continue their gravitational dance independent of our presence. This highlights a profound philosophical perspective. The universe operates on timescales far beyond human lifespans, and cosmic events unfold whether or not anyone is around to see them. Ultimately, while it is impossible to predict with certainty whether humans will survive 1.3 million years, the event encourages us to think long-term about the persistence of intelligent life and the ways civilizations might adapt to cosmic hazards. It serves as a reminder that while humanity's history is brief, our species, or our descendants, could one day witness and study phenomena on scales that dwarf our daily experience. Gliese 710's flyby challenges us to contemplate our place in the universe, the longevity of civilization, and the potential for intelligent life to observe and respond to slow-moving cosmic threats. If humanity, or whatever our descendants become, manages to survive and thrive over the next 1.3 million years, the flyby of Gliese 710 will likely be met not with fear, but with preparation. By that time, civilizations could wield technologies so advanced that cometary threats may no longer pose an existential danger. Instead, they might view the incoming disturbances in the Oort Cloud as a challenge, an opportunity to test planetary defense strategies, space engineering, and even cosmic-scale operations. The first layer of preparation lies in prediction. Already today, with telescopes like Pan-STARRS and observatories scanning the skies, we can detect near-Earth asteroids and comets years or decades in advance. By the time Gliese 710 passes close to the solar system, detection technology could be millions of times more sensitive, able to map every significant object in the Oort Cloud long before its orbit is perturbed. Massive networks of space-based telescopes positioned across the solar system could constantly monitor the skies, identifying new cometary trajectories the instant they begin to shift inward. Artificial intelligence systems might then track billions of objects simultaneously, predicting which ones pose a danger with mathematical certainty decades or centuries ahead of time. Once potential threats are identified, future civilizations may turn to planetary defense strategies. Currently, humanity experiments with small-scale asteroid redirection concepts, such as NASA's DART mission, which successfully altered the orbit of a small asteroid moonlet in 2022. Scale this up across hundreds of thousands of years, and it's conceivable that we could have fleets of spacecraft capable of redirecting or vaporizing comets hundreds of kilometers wide. By 1.3 million years from now, we might employ methods that seem like science fiction today. A nuclear or fusion-powered propulsion systems could deliver immense energy to comets, altering their orbits long before they approach Earth. A directed energy weapons, such as massive orbital laser arrays, might be able to vaporize surface layers of a comet, creating jets of gas that act like natural thrusters to push it safely aside. A gravitational tractors, in which a spacecraft hovers near an object and slowly shifts its path through gravitational pull, could work for smaller bodies identified centuries in advance. Our entire swarm fleets of autonomous drones could surround a comet and reshape its orbit through coordinated impacts or controlled explosions. Beyond simple deflection, future technologies may even exploit comets rather than fear them. Advanced civilizations could treat these icy visitors as resources, mining their vast reserves of water, carbon, and organic molecules. Instead of destroying comets, humanity might capture and redirect them into safe orbits to harvest their materials for use in space habitats, planetary colonies, or interstellar travel. What we see as a hazard today might become tomorrow's greatest fuel source. There is also the possibility of mega-engineering projects on scales unimaginable today. A civilization existing for over 1 million years might construct planetary shields, massive orbital defense rings, or energy barriers capable of intercepting cometary debris before it reaches Earth. If humanity spreads into multiple star systems by then, advanced interstellar infrastructure could make the dangers of comet showers trivial. With entire civilizations dispersed across different worlds, the extinction-level risks posed by a single comet strike would diminish dramatically. On a broader level, the ability to respond to Gliese 710's disturbances could represent the maturity of a spacefaring species. Surviving for millions of years requires mastering long-term planning, resilience, and adaptability. If humanity reaches that stage, we will not only predict and prevent comet impacts, but we may also be able to reshape the dynamics of the solar system itself, creating safer environments for future generations. Speculating even further, it's possible that civilizations millions of years from now may wield technologies that border on the godlike from our perspective. Harnessing entire stars through Dyson spheres, manipulating gravity itself, or even moving planets out of harm's way could be within reach. In that context, the approach of Gliese 710 would not be a threat, but a footnote in the long history of cosmic engineering. Ultimately, Gliese 710's predicted flyby provides a powerful thought experiment. It forces us to imagine what kind of species we might become. Will we still be vulnerable, clinging to Earth and fearing every rock that crosses our path? Or will we have risen to the level of a Type 1 or Type 2 civilization on the Kardashev scale, one capable of mastering planetary and stellar energy, ensuring survival against cosmic dangers that once seemed insurmountable? The truth is, the future technology to defend against comet impacts already lies within the realm of possibility, even if it is far from our current capabilities. Given enough time, determination, and survival instinct, humanity could become a species for whom even the most powerful stellar encounters hold scientific value rather than existential fear. When we talk about Gliese 710 and the comet storms it may unleash, it's easy to get caught up in the drama of a distant, star-driven cosmic threat. But here's the sobering truth. The danger posed by Gliese 710 is real yet unimaginably far in the future. We have about 1.3 million years before it makes its closest pass. In contrast, the threats facing humanity today are immediate, tangible, and escalating with each passing decade. Understanding this difference in timescales is essential to placing Gliese 710 into proper perspective. Take climate change, for instance. The impacts are not theoretical or distant, they're happening right now. Rising global temperatures are fueling stronger storms, melting glacier, destabilizing ecosystems, and threatening food and water supplies. Entire regions may become uninhabitable within centuries, or even decades, if current trends continue. Compared to the million-year timescale of Gliese 710, climate change represents a danger looming within our lifetimes and those of our children. It is a crisis that demands immediate action, not patient observation. Then there are asteroids and near-Earth objects, NEOs. Unlike Gliese 710's influence, which may send comets raining toward Earth over tens of thousands of years, an asteroid could strike with no cosmic warning beyond a few years or decades. NASA and other space agencies currently track thousands of near-Earth asteroids, some large enough to cause catastrophic damage if they were to collide with Earth. The Chicxulub impact that ended the reign of the dinosaurs 66 million years ago is a reminder of how devastating such an event can be. Unlike the distant, slow-motion influence of Gliese 710, asteroid strikes are a clear and present danger, and planetary defense missions like DART are only the first baby steps toward protecting ourselves. There's also the looming possibility of human-driven catastrophes. Nuclear war, pandemics, ecological collapse, and advanced AI risks all fall within timescales of years to centuries, not millions of years. These are threats entirely within our own control, yet ironically, they may determine whether humanity survives long enough to even witness the flyby of Gliese 710. If we cannot navigate the next few centuries, worrying about stellar encounters a million years away becomes irrelevant. This contrast gives Gliese 710 a strange dual role. On one hand, it is not something to lose sleep over today. Its dangers are far removed, unfolding slowly over eons, leaving us ample time to develop technology and strategies to deal with the cometary fallout. On the other hand, it is an important reminder of our cosmic vulnerability. Just because Gliese 710's encounter is distant doesn't make it less meaningful. It represents the kind of external, uncontrollable forces that shape the destiny of planets and species over astronomical timescales. In fact, one might say that Gliese 710 is less a warning of doom and more a call for perspective. It forces us to recognize that while we wrestle with immediate problems like climate change and asteroids, the universe continues moving on its vast clock, unconcerned with our struggles. If humanity can survive the challenges of the present, then we'll almost certainly be prepared for the comet showers of the future. But if we fail to solve today's crises, we'll never have the chance to confront the ones written in the stars. So in the grand scheme, Gliese 710 isn't the threat that should keep us awake at night. It's a reminder of the scale of time and the importance of building a civilization resilient enough to last until then. Our immediate enemies are of our own making: carbon emissions, unchecked exploitation of resources, and near-Earth objects we already know are circling close by. Gliese 710 tells us where we might be vulnerable in a million years, but climate change tells us where we're vulnerable right now. In short, Gliese 710 matters because of the perspective it provides. It teaches us that survival as a species isn't just about overcoming today's problems, but also about preparing for the cosmic ones. However, the cosmic ones will only matter if we manage to endure the self-inflicted ones first. When people first hear about Gliese 710's approach, their immediate reaction is often, "Why should we care? It won't happen for 1.3 million years. Humanity may not even exist by then." It's a fair question, but it also misses the deeper point. Astronomers study events like Gliese 710's flyby not because they are immediate threats, but because they unlock critical knowledge about cosmic dynamics, planetary defense, and the larger story of our solar system's place in the galaxy. First, understanding Gliese 710's trajectory is part of the broader science of stellar motion. Every star in the Milky Way is in constant motion, orbiting the galactic center and weaving through the gravitational tapestry created by billions of other stars. The Sun itself is moving at about 828,000 kilometers per hour, 514,000 miles per hour, around the galaxy. By tracking stars like Gliese 710, astronomers learn not only where individual stars are headed but also how stellar neighborhoods evolve over time. Studying such encounters helps refine our models of galactic dynamics, which in turn improves our understanding of the Milky Way as a whole. Second, Gliese 710 provides a real-world example of stellar encounters with the Oort Cloud. The Oort Cloud is still a theoretical construct. We've never directly observed it, but indirect evidence suggests it exists. If Gliese 710 really does pass through or near it, then it gives us a natural laboratory for studying how external gravitational forces disturb comet reservoirs around stars. It's not just about our solar system, either. If Oort-like clouds exist around other stars, then stellar flybys could play a role in shaping planetary systems throughout the galaxy. By predicting Gliese 710's influence, astronomers can begin to answer larger questions. How often do comet showers occur? How important are stellar encounters in triggering impacts on planets? Could they influence the evolution of life itself? Third, such predictions are a test of astronomical precision. Being able to say, with high confidence, that a star 63 light-years away will pass within a few thousand AU of us in 1.3 million years is an extraordinary demonstration of scientific capability. It shows how far our tools have come, from Gaia's pinpoint astrometry to the complex models that account for the gravitational pull of countless other stars. If we can predict Gliese 710's path over a million years, it means we're also getting better at predicting the movements of near-Earth asteroids and comets, which matter on much shorter timescales. In this sense, studying distant events helps us hone the very tools that may save us from closer, more urgent dangers. There's also the fact that astronomy operates on cosmic timescales. Human lives are short, but the universe unfolds slowly. To understand our solar system's past and future, astronomers must think in spans of millions or billions of years. Studying Gliese 710 is part of this long view. It helps us see that the solar system is not a static place, but one constantly influenced by external forces. It has faced countless stellar encounters before, and it will face countless more. By identifying one with precision, we're beginning to connect the dots of these invisible interactions that shape planetary history. On a more philosophical level, studying Gliese 710 reminds us of our fragile place in the cosmos. It's humbling to realize that our entire solar system can be affected by the slow drift of a star passing far, far away. This is a reminder that Earth's environment is not only vulnerable to internal disruptions like climate change, but also to forces on a galactic scale. By looking ahead millions of years, scientists give us perspective. Survival and flourishing aren't just about managing today's crises, but also about becoming a civilization that can withstand the vast sweep of cosmic time. Finally, there is a practical reason. The methods developed to track Gliese 710's journey have spin-off benefits for current science and technology. The data from missions like Gaia improves star catalogs, refines navigation for spacecraft, enhances our ability to detect exoplanets, and deepens our understanding of stellar populations. In other words, the pursuit of distant knowledge produces tools that improve our immediate capabilities. So, why study this now? Because astronomy is not just about the present moment. It's about learning to read the universe's clock. By studying Gliese 710, we are not simply cataloging a future event. We are building the framework to understand how stars, planets, and comets interact across millions of years. That knowledge not only enriches our science, but also strengthens our ability to face both current and future cosmic challenges. As we come to the end of this journey into the future encounter with Gliese 710, it is worth pausing to reflect on what it truly means. This star, quietly drifting toward us across the void of interstellar space, is more than just an astronomical curiosity. It is a profound reminder of our vulnerability in the universe. Think about the scale of what we've explored. Gliese 710 is not a giant, fiery supernova waiting to explode. It is not a monstrous black hole threatening to devour our system. It is a relatively modest star, smaller, dimmer, and less powerful than our own Sunday. Yet even this unassuming traveler, by merely passing near us, could reshape the delicate architecture of our solar system's outer edges, stirring ancient comets from their frozen orbits and sending some of them careening inward, toward our fragile planet. This vulnerability is not something unique to Gliese 710. It is a truth of existence. Earth is a small, rocky world orbiting a single star, itself one of hundreds of billions in a vast galaxy. Our safety depends on a lucky balance of orbital dynamics, a relatively calm galactic neighborhood, and the absence of catastrophic encounters in the near term. But Gliese 710 shows us that the cosmos is not static, not serene. It is in constant motion, and in that motion lies both beauty and danger. For humanity, this knowledge should be both humbling and motivating. Humbling, because it reminds us that no matter how advanced we become, we remain subject to forces far beyond our control. A passing star millions of years from now can disturb icy bodies at the edge of our solar system, creating threats we may not be able to prevent unless we have evolved into a civilization with extraordinary foresight and capability. Motivating, because awareness of these dangers pushes us to think bigger, to prepare not just for the next decade but for the next epoch. Gliese 710 is a mirror of our impermanence. Dinosaurs once ruled Earth, but a single cosmic impact ended their reign. Humanity, too, exists at the mercy of cosmic chance, unless we develop the wisdom and technology to change that destiny. Will we still be here in 1.3 million years to witness Gliese 710, blazing as the brightest star in the night sky? That depends not on the star, but on us. On whether we solve our current crises, whether we build resilience, and whether we see ourselves as more than just passengers on this fragile blue world. Ultimately, Gliese 710 reminds us that Earth is not an island. It is a tiny part of a much larger cosmic web, influenced by stars, comets, and forces that operate on timescales far beyond our own. In that light, every step we take to safeguard our planet today, against climate change, against asteroids, against our own destructive impulses, becomes part of a much greater mission, the mission to endure as a species long enough to see the grand events of the cosmos unfold. So the lesson of Gliese 710 is clear. The universe is vast, dynamic, and indifferent to our survival. But by studying it, by preparing for it, and by understanding our vulnerabilities, we carve out a measure of control within that vast indifference. This star is not our enemy, it is our teacher. It shows us the fragility of our existence, yes, but also the astonishing resilience and potential we hold if we rise to meet the challenge of time. In the glow of this future flyby, humanity faces a choice. Will we vanish like so many species before us, or will we endure long enough to look up at the sky 1.3 million years from now and say, "We knew this was coming, and we were ready"? This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.